Good morning, sir.
Yeah, good morning, Firoja. Am I audible?
Yes, sir, you're audible, sir. So right now we are having
Okay.
156 attendee joined. So, sir, can we take another
Yeah,
5 minutes so that rest of the
yeah,
people
yeah,
will also?
sure. We can wait some more time. I think
Okay.
what is the total number of registrations?
So total it will be around, we will be having around 500 to 600 people joining today. But the actual count, sir, we will inform you after the event start because we are waiting for
Yeah,
the
yeah,
final result from other academies.
yeah, yeah. So we will wait a couple of moments some more because otherwise it will be difficult, right?
Yes, sir. Yes, sir. Okay.
Okay.
Thank you, sir.
Hello, good morning, Firoja ma'am. Hello.
Yeah, good morning, sir.
Yeah, good morning, ma'am. We have sent a new list in today's morning. 4 more candidates are added on that list.
Yes, sir. So we have seen the list, sir. So we requested everyone to please share. We have given in the WhatsApp group also, we have shared the attendee list. So
Okay,
once
ma'am.
the event is start and the inauguration is over and we start with the session, then we will one by one, we will be adding the participant.
Okay,
So I
okay.
request you, sir, please, if possible, you can share the attendee list right now. They can join the event and later on we will be
Yeah,
updating the list. So that,
we will send, ma'am, all the participants. So
yeah,
we will
sure.
also.
Thank you, sir.
Yeah,
Yeah.
yeah.
Thank you, sir. Thank you for the support, sir.
Okay, welcome.
Good morning.
Good morning, sir.
Yeah, Firoza, you please check the website. Actually, in our website,
Yes, sir.
uh, my mobile number is given. Gaurav's name is there and my mobile number is there. Can you please correct it? Because
Okay, sure, sir. I will just check once again, sir.
go to
Thank
our
you, sir.
E&ICT website and their courses, winter courses.
Okay.
Gaurav's email ID is there, but my mobile number is there. And that's why possibly people are calling me.
Okay. Okay, sir. Okay, sir, we will correct it, sir.
Mhm.
Okay. Thank you, sir. Good morning, Gaurav, sir.
Yeah, Pooja.
Sir, Vineet Sahula, sir, has joined, sir, and we are having
Okay.
almost 261 people, and Ratnajit, sir, also joined. So
Yeah.
I will check
So we
for
move to 2
Bharat,
more minutes and 9:40. You please start.
9:40, na, sir?
Yeah.
Okay,
Good
sure.
morning, Gaurav.
Okay.
Good morning, Professor
Thank you, sir.
Bhattacharya.
Namaskar, Saula sir.
Sorry, joining late.
Ah,
I forgot actually. Please.
Pooja, you
good
will be
morning,
coordinating
Professor
the
Savla.
Good morning, sir. Good morning.
Good morning.
नमस्कार आदि सर.
नमस्कार, नमस्कार. आपके नाम है, मेरा मोबाइल नंबर है, वही फिरोजा को बताया है.
Welcome, Gaurav Jalan. Good morning.
Good morning, sir. Good morning, everyone. Happy to be here.
Yeah.
Good morning, sir.
Good morning.
Morning.
Nallam, are we having meeting today? Hello? Oh, Sunday. Okay. Okay. Yes, Sunday, okay. Sunday कितने बजे? Sunday at what? I scheduled. Firoza, are we starting the event?
Yes, sir. Sir, Aprajita ma'am is joining in few minutes, and sir, we are trying to contact Bharat sir also.
Okay.
May I request Balchand Nagar sir to please confirm if Bharat sir is joining?
Okay, ma'am. Okay, ma'am. I will try.
Yeah, sure. Thank you, sir. We are trying to call him, but the number is not connecting.
Okay.
Okay, thank you, sir.
So, Firoja,
Yes, sir.
can you please start because almost 300 participants have joined. So we
Yes,
can
sir.
start now.
Aprajita ma'am is joining, sir.
Okay, okay. So
So
we will
should we
wait for.
wait, sir?
Yeah, yeah. We wait for 2 minutes and then we join. Then
Okay,
we
sure.
start.
Thank you, sir. Thank you, sir.
Okay.
Hello, Firoja, ma'am.
Yes, sir.
Hello.
Yes, sir. Please, sir. Hello, sir.
Hello. Yeah. Goro, sir.
Yes.
Yes. Good morning, sir. Balchan Nagar from
Morning.
NIT Patna.
Yeah, namaskar, namaskar, Balchan ji. How are you?
Sir. Sir, fine, fine, sir. Sir, Bharat sir is not joined, sir, due to some
Okay.
reasons. He said. Yes.
Okay. Okay. No problem.
Sir. Okay, sir.
Aditi, I just received an email from Aprajita ma'am. She is finding trouble in joining. Like she wrote me message, it is not allowing me to join. So can you send one invite link right now to ma'am, and when ma'am join, we can add her in in panelist list.
Yeah, sure. I'm doing that. Thank
Yeah,
you.
sure. Thank you, Aditi.
Hello. Hello, Furoja.
Yes, sir.
Hello. Yeah,
Yes, sir.
Professor P.N. Kondekar joined, but he is
Okay.
getting added to attendees. So can you
Okay,
please
sir.
to the panelist?
Yes, sir. Yes, sir. Please, sir. We are doing this. Aditi, please move Ponikar sir to the panelist group.
Yeah, sure.
Thank you, sir.
Joined?
Ma'am, the ma'am is facing some issue.
Good morning,
Just
everybody.
I think.
yeah.
Good
Okay.
morning,
Ma'am
everyone.
joined. Yeah.
Good morning,
Yes, sir.
Gaurav. I have also
Namaskar, ma'am.
joined.
Good morning.
Namaskar. A very good morning and a very good luck to all the participants and to the organizers. I'm sure
Very
that
good
all of
morning.
you are going to, yes,
Very good morning.
have a good time. Thank you. Thank you, Professor Savila. Good morning.
So,
Good morning, sir. Sir, can we start, sir? So, a very good morning to all the respected expert dignitaries, participants, our coordinators. On behalf of E&ICT, Electronics and ICT Academy at IIT Guwahati, MNIT Jaipur, IIITDM Jabalpur, NIT Patna, IIT Kanpur, IIT Roorkee, we would like to invite you all for this 2-week online faculty development program. We will be starting with the inaugural session. So we would like to invite Dr. Gaurav Trivedi, sir, the principal coordinator for this program, to please start with the inaugural session. Sir, please, sir.
it's me, Furoja.
Yes, sir. Yes, sir.
Hello. Yeah. Yeah. So, welcome everyone. I thank all the, you can say, participants to register this course. First of all, during this COVID-19 pandemic and seeing their overwhelming response, I hope that we will be having a lot of, you can say, it's onus on us to, you can say, deliver a high quality course, and we will try our best to do that. I also thank Professor Vineet Saula, Professor Parajita Oja, Madam, and Professor Bharat Gupta, Professor Balchan Nagar, Professor Meena Pachore, Professor Pranav Pushpadatta, Professor P.N. Kondekar to make this course, you can say, and you can say to and to decided to, you can have to popularize this course really a lot, so that we are having more than 600 registration in this single course. Due to their it was possible only due to their you can say the genuine effort. We are able to we are having a very good number of sanitation pan-India. At the same time, I also thank Professor Ratin Bhattacharya, who is the PI of this academy, and who is like me being a junior faculty and like guiding me throughout. He has made you can say a lot of his suggestions really become a lot of you can say fruit bearing for me for this course. So Rafi sir, really a lot of thanks to you, and a lot of thanks to Froja and Aditi to you can say bear my eccentricities and working late nights to all these courses. So with this, I thank everybody to you can say arrange to gather a large number of participation, and we hope that together we will be able to make this course really a success. I thank once more to Professor Vineet Saula and Dr. Bhuchandani to you can say to request one of the stalwarts in the country like Professor Pityendra Panda, Professor Anshul Kumar, Professor Balakrishnan from IIT Delhi, Professor Sarangi from IIT Delhi also to deliver you can say keynote in this particular course. So we are very much delighted to have all the expert you can say expert panel in the area of computer architecture and a well-known expert on the computer architecture to deliver their lectures in this course. So thank everybody. Professor Pitendra Panda, I am seeing, so a very much warm welcome to you, sir. And I believe that your presence will really enlighten all the participants here. And last but not the least, I thank Mr. Puneet Mittal and Dr. Aditya Dalakoti to share this course with us. And I believe these two young people who really have such a nice experience from the industry and all, will deliver the course, and all of you will really enjoy. So thanks everybody to be here and to be the part of the journey, which will go for next 10 days. Thanks once again, and I pass the baton to Ms. Pooja for further processing. Thank you.
Good morning, Professor Panda. We welcome you on behalf of all Organs Committee.
Thank you, Professor Trivedi and Professor Savla. Yeah, it's a pleasure to be here. Please go ahead.
Thank you, Gaurav sir. We would like to invite our principal coordinator, Professor Ratnajit, to please say a few welcoming note to the participant and all the members who are connected. Ratnajit sir, please, sir.
Thank you, Firoz. I am sorry that I missed a part of this program because there was a power cut and my router is not on UPS. So sorry to join late. It's an initiative from 4 of our academies together, IIT Guwahati, E&ICT Academy, MNIT Patna, MNIT Jaipur, and IIITDM Jabalpur. So this E&ICT academies together, we are trying to host this type of courses for quite some time now. And this has been very successful in terms of number of participation and the ranges of expertise we get, because today also I was just listening to Gaurav, and we have a galaxy of stalwarts in this area who will be sharing their expertise with our faculty colleagues spread over different parts of the country. And I feel very, very excited whenever we conduct this type of joint FDPs, because this is a platform where we exchange our thought, we learn from each other. All of us, majority of participants, we are faculty members, and we follow the lifelong learning process. And this platform gives us an opportunity to discuss, deliberate with the best of the people in the country in their respective areas. So I welcome all the dignitaries, the experts, my fellow colleagues from different institutes who have taken out time to join this program. And I hope with the coordination of the 4 participating academies, because we are working together for a long time, we will have a very nice course. And I wish that next 10 days of interaction remains very, very fruitful for everybody. With these few words, I wish best of luck to everyone. Thank you.
Thank you, sir. Thank you for the welcoming word, sir. Now we would like to invite Professor Vineet Sahula, sir, the Chief Investigator from MNIT Jaipur, to please welcome the participant for this event. Sir, may we request you, please?
Yeah, thank you, Furuja. At the outset, I will just thank and congratulate Professor Bhattacharya and Professor Gaurav Trivedi at IIT Guwahati for putting such a nice course for last 2 years. I think it's the 3rd or 4th in series, almost going to digital flow for synthesis, and that too on the open source. That is a great achievement, doing everything on open source. And I should also thank all the speakers having kindly agreed to actually interact with the participants and join us in the cause of education, spreading that through open source that way. So I'm happy in the coterie and the company chair of my own chief investigators, Dr. Bharat from Patna, Dr. Trivedi and Dr. Bhattacharya from Guwahati, Madam Ojha from Jabalpur and other academies. But I have learned a lot in last 4-year journey of our offering these courses, as we have taken lead in offering various formats of these courses all along the 4 years. I think this is a 3rd or 4th type of a format in there. And thanks by heart to all the speakers who are present here and who are going to deliver talks in the next 10-12 days. And I welcome all the participants and wish them a good learning through the course. Thank you very much.
Thank you, sir. So we would like to invite Professor Aprajita Ahuja, ma'am, the Chief Investigator of IIITDM Jabalpur, to please say a few welcoming notes and to please welcome the participant. Aprajita, ma'am, maybe. Aprajita, ma'am, we request you to please unmute.
Good morning to all of you. Thank you so
Good
much.
morning, ma'am.
And a warm welcome to all the participants. It has been such a beautiful journey of working together of all these academies. Professor Gaurav Trivedi and Professor Sahula have been conducting these courses for a long time. And I'm happy that there is a good gathering of participants and our experts. Professor Ratnajit Bhattacharya has also blessed the participants. As Professor Bhattacharya says, that it is such a good learning experience. We learn from each other. And for last several years, as Professor Sahula says, we have been trying to work together on these. And this particular experiment has been very successful. So I'm sure that all of you are going to have a wonderful experience, a good learning experience, and good takeaway from this program. My colleague, Dr. P.N. Konde, also joins me in welcoming all the participants from IIIT Jabalpur. Thank you so much, all of you.
Thank you, ma'am. Today, due to some engagement, Professor Bharat Gupta sir from the CI of MNIT Patna could not join us. So we request Chand Nagar sir to please say a few words to the participant.
Okay. Good morning, ma'am. I Balchan Nagar from MNIT Patna. I am very good morning to everyone and present here, our respected dignitaries, our expert speakers, and warm welcome to all of our participants, our coordinators to attend this FDP on the RISC-V VLSI implementation from RTL to GDS flow. and I hope all of you are enjoying this. We have got a very good registrations, over 261 participants. So thank you all the participants for believing us, and I hope we all are enjoying the sessions. Okay. So thank you everyone. Thanks.
Thank you, sir. We are having coordinators from different academies who have helped us in getting such a good participation. So we would like to invite Professor P.N. Kondekar, sir, from IIITDM Jabalpur to please welcome the participant. Sir, please.
Oh, thank you. Thank you. Thank you. Firoza madam, thank you very much. Am I audible?
Thank you, sir. Yeah. Yes,
Yeah.
sir, you are audible, sir.
Yeah, I would like to first of all welcome all the participants, and also thanks all the panelists for taking out time to update our knowledge in this field, which is a very important field nowadays. And the efforts by all the coordinators has excelled in enhancing the number of participants, which is the great aim. And under this pandemic situation, having such a great number of participation in most of the courses, particularly nowadays, the software related courses also has a great participation, but our core area, which cannot be underestimated, is also very important. And now the people have started understanding, and definitely it's a core area and very important for learning. And electronics and communication and chip designing is the base for all the even software related, so embedded system and all that will be dealt with here. And I'm sure all the participants will get immensely benefited by attending this course. So I wish and welcome all the participants to greatly enhance and also take keen interest in attending this throughout this course. Thank you very much.
Thank you, sir. So we would also like to invite the coordinator from MNIT Jaipur, Professor D. Bul Chandani, sir, to please address to the participant. Sir, please.
I think Dharmendra may not be there. He has gone to Haridwar for his last rite of his father-in-law.
Okay,
Bharti
okay.
might have joined. I think we can go ahead possibly. Bharti also
Okay,
is
sure.
a representative. I'm representing both of them. Thank you.
Firoza,
Yes, sir.
please invite the experts to speak a few words.
Yeah.
I think
Yes,
Professor.
Professor Panda is there, and
Yeah,
yes, sir. Yes,
Puneet
sir.
and
Yes.
Aditya, Puneet and Gaurav, I think they are.
Yeah, that
Yes,
Professor
sir.
Panda.
Yes, sir.
Professor Panda.
Yes, sir. So we would like to invite Professor Panda, sir, to please say a few words to the participant.
Yeah, thank you very much. It's a pleasure to be here. It's a deep honor to be part of these proceedings. I understand this is a huge amount of work that's involved in coordinating such a major event. I'm not sure this. Let me just turn that off.
Yeah, you are not visible, Professor Panda. Your video, I think.
We can hear you, sir, but we cannot see
We
you.
can hear you very well.
Okay. Yeah, it turned out that that there are two cameras on this laptop, and it was pointing the other way towards the.
Please carry on.
There were just too many options, and enough automation is not there to realize which camera to use. Yeah, thank you for pointing that out. Yeah, as I was saying, it is sometimes easy to underestimate some of the huge organizational effort and coordination effort that is involved in putting together a program like this. Congratulate all the organizers. Many of them have been friends of mine for a long time now. So it's really nice. While the circumstances are very exceptional, maybe some of the positive aspect of it is that being able to connect from any place actually is in some way an advantage, because we are able to have a much larger gathering. That's really heartening. It's some good news in all the gloom that is there everywhere in the world today. So it's really a pleasure to be part of the meetings. The topic itself is extremely exciting, and I was really happy to see that open source platforms are being used as the experimental vehicle to study all of these chip design aspects, and they are being headed by people with significant industry experience. So that's a very rare kind of opportunity that in academia we often don't have. That's really nice. And also, of course, I would like to follow up since I have more later on coming. I won't say much, but in fact, all the other research that we are all doing in academia also is based almost completely on open source platforms. So if one of the things that we will take away from course like this, of course, that we having gained the experience on these open source platforms, and after being convinced that in fact
Excuse me, sir. Sir, your voice, sir, your audio is not clear, sir.
Firoza, I suppose there are two logins. I do not know, because another login you can see PP. I think that is
Yes,
creating the
sir.
problem.
the technology is actually there, it's available to all of us. So to be able to properly exploit that. So I suppose that comes out as the course, the curriculum is built for this technique. So yes, thank you again for inviting me. I look forward to interacting with you.
Thank you, sir, for your welcoming words, sir. So we are having with us our expert, Gaurav Jalan, sir, Dr. Gaurav Jalan, sir. So we would like to invite sir to say a few welcoming words to the participant.
Sure, thanks, Firoza. Just correcting, I'm yet to receive a doctorate. So yeah, I'm Gaurav Jalan, representing the industry here. I really congratulate the organizers in enabling this excellent platform to foster the culture of learning. I completely resonate with the thoughts of Professor Bhattacharjee that life is a journey and it is continuous learning that feeds this journey. I'm honored to be part of this elite group, and I really look forward to participating actively to it. Thank you so much.
Thank you, sir. We are having with us our expert who will be carrying forward the session, Mr. Aditya Dalakoti, sir. So we would request Aditya, sir, to say a few words, sir. Please, Aditya, sir.
Hello, everyone. Really, thank you for the academies to organize such a wonderful program, and all the coordinators to manage it so well with a large amount of attendees and panelists. It is quite difficult, and such a great job has been done. Really, thank you for that. And apart from that, with respect to the program, as already mentioned by all the dignitaries here, from the academics and industry. The idea is to have open source platform to enable academicians and also industry people in India to use those platforms and make something meaningful out of them and make products out of them. How do we go from just fundamental concepts in which are in the literature to something meaningful, which will help going forward India and world both. So that's the general idea, and taking an open source platform for that that helps academics. And so that's where we'll proceed. And the idea is to have multiple RISC cores and take them through the whole VLSI implementation flow. I will talk more as we go through the course, and I have some introduction slides later on the same aspect. Thank you. Thank you, Firoza ma'am.
Yeah, thank you, sir. We are also having with us Mr. Puneet Mittal, sir. So we would also request Puneet Mittal, sir, to say a few words to the participant. Puneet, sir, please.
Thank you, Firoza ma'am. So first of all, thanks everyone, and thanks all the panelists and all the attendees. And just checking, it's like 401 participants, so it's a huge number, and I'm sure like it's a huge responsibility also. Like we should be able to meet all of your expectations. So we will talk about the whole program in detail, and I have a follow-up session today itself. So we will discuss at that particular time. But right now, I would just say, as a industry person, or you can say like as a deliver, because I'm going to deliver. Like stay tuned, and just it's a 10-day exercise, and I'm 100% sure like you will get a lot of things out of this. Thanks a lot, everyone.
Thank you, sir. We are coming to the end of the inaugural session. So we would request Gaurav sir to please conclude the inaugural session. We will start with the keynote speak for today. So I request Gaurav sir to please conclude the session. Gaurav sir, please.
Thank you, Firoza. Thanks everybody, all the panelists, our expert, Professor Pritinjan Panda, Professor Mr. Gaurav Jalan, our other expert, Mr. Puneet Mittal and Dr. Rajendra Koti. I hope that I'm to say this is, as you rightly said, that this is really a this is actually our endeavor to you can say take RISC-V you can say knowledge to as many people as possible. And I would say we have, precisely that IIT Madras has already designed a RISC-V based Shakti processor and all, but still there is a lot more ways to go. Okay, and the dream of actually having our own completely you can say CISC processor, okay, like the Pentium also will be realized, okay, in near future, okay, if we all put a good amount of efforts. So this particular course is I'm not saying it is sufficient, but definitely it will motivate a large number of people to work in that area, and will motivate them to build products based on the RISC-V processor and contribute towards Atmanirbhar Bharat. So with this, I thank everybody to grace the occasion. Professor Ratni Bhattacharya, Professor Vineet Saula, Professor Aparajita Oja, Professor Praveen Kondekar, Professor Balchan Nagar, and I think I have Professor Pritinjan Panda once again, Professor Meena Pachore, Mr. Puneet Mittal, Mr. Gaurav Jalan, and Dr. Rajendra Koti to grace the occasion and kick-start the course. And with this, I request Firoza, I think this is we are having our keynote speech by Professor Panda back immediately after this inauguration, right?
Yes, sir. Yes, sir. Yes, sir.
Yeah. So I request Professor Vineet Saula to please introduce Professor Pritinjan Panda and start the technical sessions. Thank you. Thanks everybody. Thanks all the course coordinators from different colleges. And thanks all the participants. Without your active participation, this course will not be a success, and so it is very much required. And since COVID is still there, so stay safe and stay healthy, and wish you a very good luck. Thank you. Professor Saula, I request you to please now take the dais. Thank you.
Thank you, Gaurav, for giving me this privilege. It's really a privilege and a great pleasure to introduce Professor Preeti Ranjan Panda Sahab. He is currently head of School of IT at IIT Delhi and a professor in computer science and engineering. I have a brief work description about him. I would I will ask excuse if I am missing anything about him. He's a great accomplisher. He's a very enthusiastic teacher and very diligent researcher, as evident from his writings in various journal papers and books. Professor Preeti Ranjan Panda received his BTech degree in computer science and engineering from Indian Institute of Technology, Madras, and his MS and PhD degrees in information and computer science from University of California at Irvine, US. He is currently a professor, as I let you know, professor in computer science and engineering at IIT Delhi, and also heading the School of IT additionally at IIT Delhi. He has previously worked at various industries, Texas Instruments, Bangalore, Advanced Technology Group at Synopsys, Mountain View, US, and has worked as a visiting scholar at Stanford University in the past. His research interests are into embedded system design, CAD VLSI, post-silicon debug and validation, system specification and synthesis, memory architectures and optimizations, hardware software co-design, and low power design. He is author of two very prestigious books, one with Kluwer and another with Spinger, Memory Issues and Embedded Systems on Chip, Optimization Explorations. It is from Kluwer Academic Publisher. Another book is on titled Power Efficient System Design from Spinger. He is recipient of prestigious IBM Faculty Award and Indian Semiconductor Association Techno Mentor Award and the Department of Science Technology Young Scientist Award. Research works authored by Professor Panda and his students have received several honors, including Best Paper nominations at CODES and IIIS. It is a symposium on system synthesis and co-design workshop, DAT DATE in Europe, ASP DAC in Asia, and VLSI Design Conference, and most downloaded paper mention of ACM transaction on design automation. Professor Panda currently serves as editor-in-chief of IEEE Embedded System Letters. He has served earlier on editorial boards and is serving on editorial boards of many journals like IEEE Transaction on CAD of Circuits and Systems, ACM Transaction on Design Automation of Electronic Systems, IEEE Embedded Systems Letters, IEEE Transaction on Multi-Scale Computing Systems, and International Journal of Parallel Computing. He has been Journal Co-Chair of VLSI Design and Technical Program Co-Chair of CODES and IIIS workshops, very prestigious workshops internationally, and at TPC of International Conference of VLSI Design and Embedded Systems in India. He has also served on technical program committees and chaired sessions at several conferences in the areas of embedded systems and design automation, including DAC, which is the epitome conference of VLSI in the world, DAC, ICCAD, DATE, Codes and IIIS, IPDDS, ASP DAC in Asia, and EMSoft. This is all I have, and I have hurried through his biodata. It's a longer one. I beg your pardon, Professor Panda, if I miss anything. We all welcome you for your keynote address now. Thank you very much for being with us.
Thank you for the kind introduction, Professor Saula. Start off. I think I know what the schedule for today is. I'll try to stick to that to the extent possible. Let me try to share the screen. Okay. Is the screen visible? And if there's window,
Yeah, slides are visible. Yes, please, they are visible. Only your voice is slightly low.
Okay, fine.
Maybe mic, you can close to mic.
I should be closer.
Thank you very much.
Okay, thanks, Professor Saula, and thanks for the kind introduction. And it's nice to see and meet colleagues online. It's great to see all this activity happening and so much interest in these technologies, in the platforms, in the open source platforms, and the choice of taking an open source processor instruction set architecture like RISC-V and planning to implement large parts of that through the VLSI design flow. I think it's a great idea. It obviously is the result of a lot of planning and deliberation. I would like to congratulate the organizers for that. It's really appropriate. It's an opportunity to tie many different levels of abstraction of the design flow, but it is great that on one extreme we are talking about layout and synthesis and timing analysis of circuits, and but also getting the bigger picture ultimately of a complex processor like RISC-V, all of them that are involved in the process. I think it's a great learning experience. I'll try to position the main content of this talk with respect to what's coming up later on. The objective is to discuss a little bit about the emerging memory technologies. A lot of very exciting stuff is happening in this space. Newer devices are being explored by engineers, and one of our objectives here in this talk is to clearly establish what is the link when device engineers come up with a new device. There are a number of levels of abstractions, layers of abstractions that take us from that all the way from the device to a large chip in which billions of such devices might be there. So we'll focus on the memory technologies. That's where a lot has been happening in recent times, and take it all the way to system level design. How does it impact larger systems? That is really the flavor of this talk. Hopefully through this we can develop an appreciation of that connection. Now that these new kinds of circuits, new kinds of devices, they are available, what does it mean for us if we are looking at it from the other end of the spectrum, where we design a processor with memories, large systems, system on a chip, and so on? Where is the connection? What are some of the interesting opportunities and challenges that come up in the process? That's what we will try to talk about. I don't know if there is a mechanism for people to ask questions, and maybe it gets relayed in some ways, but I'll be happy to take any questions or clarifications through this presentation. Okay, so let's move on.
The questions will keep coming from chat and question answers. I think we'll collect them for you. Anyway.
Okay. Okay, please. Yeah, I'll be happy to be interrupted with any kind of questions. I realize that the participants may not be able to directly speak, but if it comes through chat and you see something feel free to interrupt and ask a question. Okay, so here's the motivation. First of all, why are we talking about it? Where is the opportunity? Let's just define the big picture. But most of the time we will spend in sort of two directions that are considered promising nowadays with respect to the next generation memory. Those are non-volatile memory and 3D memory. The motivation itself actually should be very clear. It does not it does not require too much effort to see that to see where this motivation comes from. Why are we looking for a next generation of memory? So here's an example. This is what is called the M1 chip. It's one of the recent chips that came out of Apple and going into the Apple products. So what you see on the left here is a die photo of that chip with some of the things being marked. There's a GPU, there are a bunch of processors. Some are high performance processors, some are low power processors. There is an AI accelerator inside there, and so on. This is just an external annotation that other people have done. The source of this particular annotation is IIITDM. That's where I've taken it from. But this picture, this overall diagram, that comes from Apple itself. This is just some conceptual picture that shows, there are CPUs there. There is an interconnection network. There are GPUs. There is that AI accelerator. All of these things are part of this. There are levels of caches, and finally there is a DRAM. So yeah, that's what that picture looks like. That it is M1, this particular chip is actually besides the point. This is just an example, but not very different in terms of what we are going to be talking about here with respect to the relevance of memory. Now, where is memory in this picture? If we are going to put it up now, this is just some high-level photo of the die. It's not at all clear what is where, and of course that is not revealed for us. But in fact, even this logical diagram by the manufacturer reveals a lot of things. Physically, we see what's going on in that picture. But there is a CPU. Actually, even if you just take a look at that CPU box right here, there are 12 MBs, 12 megabytes of L2 cache. That's what this is. This is it's anybody's guess, of course, but that thing in the middle is probably what is that cache. Around this are these processors. Anyway, that's one part of the chip. Similarly, if I look at the other bunch of processors, that too would have some cache memory. There is some other SLCs, this single cell. Finally, there is that AI processor. That too. Now, that's one. Then there is the GPU. So you can say that there is compute power in there, which is what the processor is. Maybe more of that you will actually be studying in this course when we take a look at what's happening inside the RISC-V. But the answer to the question, where is the memory in this picture, in fact, is that it is everywhere. It is there inside the CPU. Large parts of the CPU are just the memory. GPU, same with the GPU. And the same with the AI accelerator. All of these are dealing with large amounts of data. These are data intensive applications. So there is, of course, a need to store that data on chip, off chip. Everywhere else there is a lot of the interconnection network. It's data that is flowing through. External to the chip, the network, it is data that is flowing through. Because there is so much of manipulation of the data, there is a need to have storage opportunities, of course, for storage of that data. Not just outside, but also inside the chip, because we don't want to go outside and fetch it all the time. So of course, we are dealing with all the data, and therefore there is a need for memory. The CPU, GPU blocks themselves, inside that they are actually full of memory, because there is this idea of a cache memory. We'll be talking more about that. We'll go down a little bit further into the architectural space, where we'll talk a little bit more about caches and so on. But it should be, of course, clear that much of these high-end SoC, not just limited to high-end, but everywhere SoCs, multi-core processors, all of these, memory plays a very dominant role in there. The other thing that is not very clear in the physical picture, but it's actually clear in that logical picture here, is that there is actually large amounts of DRAM that is located very close. This is located in the same packaging structure. So you can think of that thing that's left here as most corresponding to most of that diagram. But to the right here, you have DRAM. This is actually packaged on this is on the same package. So you can see that DRAM is actually getting closer. This is an interesting architectural innovation. Normally, it might be a little further away on the same PCB, but this is actually bringing it even closer to the CPU. So that's very nice. But of course, what is our requirement? Requirement is density, requirement is low power. We can't afford to spend too much power. All the performance that we need from the modern systems is under all of that has to be delivered under a power budget. So low power is important, bandwidth is important. So all of these are the requirements. They have been there in memory systems and processor systems and other SoC systems earlier too, but now, as we are dealing with more and more data, we're trying to do a lot of computation in parallel. The need becomes even greater. That's really the motivation, if one was needed, for the next generation memory. We need it to be denser. It's moving closer to the CPU, and therefore much of that is going to be fitting on chip, and therefore of course, I would like to increase that capacity. This is already a 12 MB cache here and a 4 MB cache here, and so quite a bit of memory is already there on chip. But yes, whatever is the amount of memory there, we need more because our applications are ever evolving. There is also the need for higher bandwidth. So all of these are the requirements. So as we look for solutions to these requirements, of course, we are exploring all over the space. Among them, the interesting ones are what if I just totally change the technology? So we can afford that. If the enough volume is there, then we can try out very different kinds of material, different kinds of circuits, devices, and put it together into what we can call a next generation memory. That's what we will go into in some depth in this talk. But the motivation, of course, should be very clear. So two of these lines are what we are going to be focusing on. One is what is called non-volatile memory. By definition, what that means is that as you turn power off to that memory, the data is still retained. That is normally not what we are used to in the normal on-chip memories or even off-chip DRAM and SRAM. If you turn the power off, then the data is, of course, lost usually. It would be in the next, the secondary class of memories. That's where when you write something like into your disk or into your flash memory, that's where when you write something, you expect that the data is retained, right? So in fact, because the density of those memories is very high, there is an effort to see whether we can bring that technology closer to our processor, maybe on the processor itself or as a replacement of the main memory. So not at the level of the disk, but what happens if we try to bring it closer to the processor is a very interesting question. And that's what we talk about. Non-volatile memory has always been there, but its use in levels of memory that are closer to the processor, like a cache memory or a main memory, that's what is new, and that's a very interesting topic. There's a lot of early work happening. Research is full of this kind of investigation, but commercial adoption is also not far away. Just to point out, people are thinking of these non-volatile memories as a replacement for the current generation SRAMs and DRAMs for use both in main memory and for caches on chip. several technologies have been tried out and are experimented with. Products are there in the market in an experimental sense, but there's a lot of research going on, and of course in the industry too there is a lot of attention being paid, and people are trying to come up with system level implementation, large processor implementations with these technologies. As of now, some of this is experimental, some of it is commercial, but there is some industry adoption. Flash memory, of course, has always been there. The memory that is there in our phones and in our light laptops, those are all of the flash memory kind. These are secondary memory, these are disk replacements. We can store files and all of the typical stuff that we store in the disk replacement. So that would be flash memory. That's, of course, has already been used, has been in use for a long time now. One level closer is this Optane class of machines. These are in production today. So that Optane is a non-volatile memory, not quite that secondary memory that is a disk replacement, but you can say it falls somewhere in between main memory and disk. So you can think of adding one more layer of hierarchy in between, and that's where it roughly belongs. Using non-volatile memory on the chip itself as a cache and so on, that I'm not sure that examples are there right away of commercial systems, but probably we are moving in that direction anyway. That's what we'll be discussing a little bit about. We'll go into some technical depth just to get a feeling for what kind of problems exist there. But it would be good to, of course, put things in perspective. We are talking about new technology. Let's, at some high level, without going too much into the circuit detail, just try to put that into perspective, just so that we understand what kind of technology we're talking about there, before we try to make it a part of a system that may have tens of megabytes of data on the chip. Before we build that entire memory system, it's good to start looking at 1 bit. What does that 1 bit look like? As it turns out, this is actually an intensely creative area. We are ultimately talking about a 0 or a 1 when it comes to a bit, only 2 values, but the creativity that is available for us is pretty much consider any natural phenomenon if you can classify it into 2 types. Whatever it is, whether it's a voltage or some current or some charge, or we'll see some other examples, but where a lot of very innovative ideas have gone into defining what is that 0, what is that 1. We have from what we have studied so far of circuits, CMOS circuits, we know that there is an association of a voltage with logical 0 or a 1. That's a meaningful thing that we already know. But when it comes to memory, because its functionality is a little more limited than a general purpose logic, there is there are a large number of different options that are available. I can take a pretty natural any natural phenomenon and convert that into a storage device. Maybe I can use pressure, maybe I can use velocity of something. Well, a lot of things could be used, and in fact we have moved in that direction. First, just the classical storage mechanism. This is just a DRAM cell. As you can see, the main device here that stores a 0 or a 1 is just a capacitor that is accessed through an access transistor. So the storage device is really just the capacitor. If it is charged, then we say it's a 1. If it is discharged, then it's a 0. You do need one transistor through which you access. So there is a need to detect, finally. There's a need to charge and discharge it in a controlled manner. There is also a need to find out what that charge is. Is it a 0 or a 1? And that is the purpose of that access transistor. That's just one bit. I can put together into a DRAM. Essentially, that consists of millions of instantiations of that one cell, and there is some coordination circuit that is an address decoder and sense amplifier and so on. There are some more details, but if I can quickly capture that here, already we are jumping several levels of abstraction. We are just saying that box there is 10 megabyte of DRAM. That's 10 million of those cells. Okay, so if it is off-chip DRAM, my processor can be here. That's processor, or it could be SoC or whatever kind of logic. These two would usually be different chips because the manufacturing processes are different. That doesn't, of course, prevent the more adventurous among engineers to try and integrate both of them in the same device. So this also has been tried. This is called embedded DRAM, where you actually manufacture that DRAM as part of that logic itself. So part of the CPU is the DRAM. Companies have tried out architectures like this. Sometimes, companies like IBM and Intel have had their last level of caches, which is a large size. In an embedded DRAM technology. So of course, this is just the classical one. There's nothing new here. This is a relatively old technology. But the newer ones are the ones that are very exciting. And here we said that it is charged on a capacitor that was the 0 or 1. This STT-MRAM, or also called STT-RAM. This refers to STT is spin torque transfer. Essentially, the technology, again, without going into a lot of detail, is just relying on a magnetization direction to store its 0 or 1, so that if they are parallel, it is maybe logical 0, if it is anti-parallel. So there is one layer here in which the magnetization is in one direction. It is in the other layer that we are doing the programming into a 0 or 1. If both are in the same direction, then it's then it could be logical 0. If both are in the opposite direction, then it could be a 1. Anyway, this is just a convention, and so that kind of a convention can be our association with 0 and 1. So here is just the magnetization direction. Like I said, you can take up pretty much any phenomenon, physical phenomenon, and encode those into zeros and ones, and there we have our memory. So that way the field is a little rife with opportunities. The one that you would choose, of course, there are some requirements, like it has to be dense. I would like to be able to store a large amount of bits, large number of bits in that memory. So somehow I need it to be high density, low power, and so on. But the phenomenon itself can be anything. Here it is a magnetization direction. Now what do I do about it? This bit line here is ultimately the same as this bit line there logically, even though the internal architecture here is the physical structure is totally different. That bit line essentially tells that you see that word line also being there. So there are some things that are common here. So irrespective of what that bit looks like inside, there is the need to interface that memory with the rest of our system, with the processor and register and ALU and so on. So the rest of it could well be after this bit line and the word line as they go out. Well, they would ultimately be interfacing with the CMOS logic and so on. But internally, they could be a lot more complex, and that's just an example. This is something that we'll spend some time on today, because that's an example of a non-volatile technology that people are actively looking at, the implications of using in an on-chip memory like a cache. It doesn't stop there. Pictorially, at least, it is a good idea to just review some of the other technologies. Phase change memory is a very interesting example of a memory that has already been adopted in part in that octane memory I talked about. So it has been commercialized. This is not on chip, this is off chip, but one can think of this as a replacement to the DRAM, or at least an augmentation to the DRAM main memory. What are we using here? What's the technology? This is a material that is being programmed to be crystalline or amorphous, and if it is in one of the states, we say it is a 0. If it otherwise, it's a 1. So it is the state of that solid that is being interpreted as the memory 0 or a 1. Like I said, it's open to us. We can pretty much say anything as long as it is efficient and dense and so on. We can use any physical characteristic, and there we have our memory. These electrodes ultimately will take us to the regular CMOS domain, but otherwise that's what it is. There is a heater. What is a heater? I mean, this is happening through some kind of a resistance, and that current flowing through the resistance is providing us the heat. If this material is heated, then maybe it breaks down, the crystalline structure breaks down, it becomes amorphous. That is bit 0, state 0, maybe when it goes back to crystalline, it is state 1. So something like that, again, without going into too much physical detail there. This is the connection, and this is the logical connection of a device like that into memory. Like I said, this is actually an ongoing area of research. A lot of different kinds of devices are being proposed. They all have very different characteristics. And one example that I just put up here is called a racetrack or a domain wall memory. Here, what you really have is essentially what's called a nano wire. It is like a wire that is stringed together like that, like it's like a filament, right? And it's divided. Each of these is a cell. I'm not going into what that cell looks like here, but I'm just showing the geometry and its alignment with respect to each other. So this is like a long filament, and what makes this very dense is that this is a vertical direction. What we are showing here, this is a vertical direction. And this is very, very compact, and it's called domain wall. Essentially, each of these cells is called a domain, and the physical property is a magnetization direction that we also saw in that STT domain, parallel or anti-parallel, capturing whether it's a 0 or 1. The domain wall refers to that separation between each of these, forming a wall. And what we have here is we would like to read and write into the, how do you read and write into that memory? There is some head that we are controlling and sending data through or reading. So this is the direction if I want to read, that's the direction of the data movement if I want to write. So what I will do is, you can think of this logically like a shift register structure, although there's not a register that's there. In the form of flip-flop. These are not flip-flop, but small devices of which we are controlling the magnetization direction. And you could think of just shifting that entire structure. The yellow refers to maybe a logical 0, and the green refers to a logical 1. So this is really a bit stream that it is capturing. And you can think of the working as follows. There is a head here. If you want to read some particular data, then you have to shift that data here until that one is aligned here, right above that read head, and then you read the value, whether it's that logical 0 or a 1, and that's where you are located. Now, if you after that, if you want to read the previous one, then you have to shift that whole structure to the left, the storage structure to the left. Not physically, it is the magnetization direction. These cells essentially they form a shift structure. So that's what the control is. To read something, we have to align that bit stream until the particular bit that we want to read is next to our read head or the write head. That's what. This is just a logical view, but I just wanted to put it up as an emerging technology that is of interest. So this is what is there at the technology level. Of course, I didn't go down too much into the device level, but hopefully we got some picture about what kind of devices we are talking about and its connection with the rest of the world, which is a digital world, all digital world. Right? Once the data goes there, they then So over there and here in the domain wall, it's that's our data and control and so on. Then we are in our familiar CMOS space in which there is logic and so on. So these are the sort of technology we are talking about. And while there is a table here that carries a lot of data, we need not go into all of it, but you can see that in many of these parameters, we are trying to put up the classical structures like SRAM and EDRAM, that embedded DRAM, along with the newer ones that are STT-RAM and PCM and DWM and so on. You can see along those parameters, if you say just compare the cell size, compare 120, these are relative numbers, with something like 2 or 4. You can see that there is a great difference in the range, so in the density, and therefore that's why these are attractive, right? Because then in the same space you can store a lot more data. But that's not all. If that were all, then it seems as though we should all move to just non-volatile memory. So it's not as easy as that, because there are some other characteristics with respect to which there are some limitations. Endurance is one of them. Endurance means, write endurance means how many times can you write into that cell. If you write too many times, maybe that cell will break down. Like we saw, these are physical characteristics, right? They are the state is continuously shifting between crystalline and amorphous in one of those PCM technologies. Material is such that if you keep reading and writing, if you keep writing and updating the status, changing zeros and ones and so on, then ultimately that device might break down and not be useful anymore. So such issues are there in non-volatile memory. They were not there in the other technologies. 10 to the power 16 is a very large number, and probably that device is not going to even last that long. It's a number of years that over which you achieve those numbers. But 10 to the power 8 is actually a relatively small number. We're talking about just 1 billion of them, and that might easily happen if it is close to a processor. Write it too frequently. That's why the PCM is not yet thought of as an on-chip memory replacement, but more like main memory replacement, or a little further away from the processor. But if you look at something like STT-RAM, you can see that it is somewhere in between 10 to the power 12. It is still possibly suitable. So that's just about write endurance. This is a new thing that was not there in the older technologies, but the newer technologies, if I want to keep them close to the processor, I do need to worry about it, and I have to do something with it. Well, there are a number of other properties with respect to speed. Some are fast. The older ones, the SRAM and all, they are fast, but the newer ones, they are very different. As you can see, reading is fast, but writing is slow. This is a very new kind of a property. We ought to be aware of this. And even though this seems like a challenge, one can actually take it as an opportunity for a system designer and for an architect, because now we know that there are some advantages to this memory. How do we get over the disadvantages? Right. So that's what this is about. Power, leakage power, and dynamic energy similarly. So there is a power related benefit. You can see all this non-volatile memory. Power is inherently low. Why? It's because we said that you could turn power off and it will still retain the data. So it doesn't take much power to retain the data. In fact, even if you make the power 0, then too the data is retained. So there are some good things there. Dynamic energy, reading and writing, that's where a lot of power is also consumed, and similar to the speed, there is also a differentiation here between reading and writing. Some of them actually lead to very nice optimizations that we will look at. There are some other properties. We need not to talk about all of them, but essentially the point is that no single technology is best along all the axis that we are interested in. These are very orthogonal things. Area is one, delay is one, power is one. All of these are very different from each other, and you can see that no single technology is best. They are all so for area something is best, for speed something else is best. That's what actually makes something like makes these technologies very challenging and very attractive at the same time. For a system designers, we ought to
exploit these things, but it is not obvious how to exploit them because they are good for something, they're not good for other things. How to go about designing our systems to inherently take into account both the strengths and the limitations of those technologies is what is the job of the system designer, the higher level system designer. So those are some of the challenges. We can take a look at some of these challenges to understand what's going on. Let's look at STT-RAM. We are saying that we use it, well, when it comes to the levels of memory that are very close to the processor core, right? We keep them SRAM because the speed is important. But when this is still inside the processor, and the later levels of the hierarchy, the further levels of the hierarchy, that the last level cache, that's when we can use STT-RAM because there the speed is not very important, but the capacity is actually important. We can make such choices. And while I need not go into all the details, all kinds of optimizations are there. If I am saying that read is cheap but write is expensive, I can look at two consecutive words like that I'm going to write into a memory. And if I see that only a couple of bits are changing, then what you could do is maybe you just read it first, read the word first, and then do something to make sure that only those two bits that need to be written, only those are written. The others don't disturb them, and that's good for for saving energy and saving time also. There are lots of other such interesting optimizations you could do. There could be a flag that indicates, you look at a frequent pattern, all zeros is kind of a frequent pattern. This happens if you have integer data, for example, all zeros or all ones. This is actually very common. Your high-end, most significant bits might actually be full of all zeros or all ones. We could exploit that in some way with just an additional flag that can tell you if that flag is 1, it means that all of these are actually zeros. I can ignore all of that, and therefore there is no need to write, and there is no need to incur that expenditure for writing all of these. Essentially, it could be that one bit can tell us that it is all ones or all zeros. So yeah, I could do some things like that. I could also do something like use some kind of intelligent coding. If it turns out that this was the old word, but this was the new word, you can see that out of the 8, these 7 actually completely flipped. Then why don't I just say, just keep one additional bit that tells me that in fact you should interpret this by complementing the whole byte, right? So that way I don't need to write all of this. This is still the same as old, only this one bit needs to be written, and that's okay. So these kind of optimizations one can think of when dealing with memories with an asymmetric property like this. The reads are easy, but the writes are not easy and expensive. Then you can try to minimize the number of writes. So this is at one level. I can try to control that at various levels. For example, writing into that cache, because the writing is expensive, right? I can see, I can ask, evaluate the criticality. Is it really beneficial? There are different kinds of write. When you store, there is some kind of write that's going on. There is, when you load from the main memory, there is a different kind of write. There is some speculative load called prefetch, which we think it's going to be necessary, therefore we fetch them in advance. So different kinds of writes I could actually evaluate and prioritize in some way. There is no need to go ahead with writes that we think are not going to be very useful. And if they are not going to be useful, then maybe we can just bypass them and not write into the last level cache. That is one way of organizing this. So, and just pointing out, of course, we won't be going into details, but the architect and the system designer, when he puts a complex system, has the opportunity to play with these kind of physical properties. Ultimately, they translate. Even though we started off with what seemed to be a very just device level what was going on, quickly we can abstract it out into a very high level design decision that is taken. You can see that since SRAM is fast, whereas STT-RAM is naturally one can think of a hybrid memory structure in which here's what you do: the write intensive lines, write intensive data, you map it to the SRAM because it is cheaper to write it. But the read intensive data that you mapped into STT-RAM, and that is an idea of a large scale memory. There is of course some management that needs to be done. There is an active data movement that I might need to do because the kind of but here is an opportunity, a system level opportunity for us to play with a hybrid structure. That way I get the best of both worlds, because if I successfully manage to do this, most of the writes are here and most of the reads are here, then I have actually managed to get an efficient system working. Right. So there's a capacity versus speed trade-off there. One can think of various various situations here. Different kinds of hybrid structures have been looked at in STT-RAM. Actually, it happens that you could change the duration for which you are doing the write. For example,
sorry,
yeah.
Professor Panda.
Yeah.
Your voice is echoing.
Okay.
Can you check?
I'm not sure.
We are getting double.
I see. Has it been happening for a long time, or it happened just now?
Yeah, please.
I think it might be first keeping our mic and speaker on.
Yeah.
So let us keep our mic on.
Yeah. It sometimes happens. Yeah, if mic, there's an external speaker somewhere else, that might happen. On my side, there is nothing else that is on. Is it still there, or?
No, it seems okay. Yeah.
It seems okay. Oh, okay, fine. All right. So yeah, there is some different kinds of hybrid structures, and one of them in this particular technology is that you can vary the duration for which you are doing the write. A normal write takes a lot of time, but you can cut it short. That affects the volatility property. It's no longer non-volatile, but maybe it is okay depending on the kind of processing that we are doing. We might not need to keep it on for too long. So that way there is a low retention part of it and there's a high retention part of it. And one can actively do the following. Again, I put the write intensive lines in the low retention because there the energy is faster, right? If it's the same power, lower amount of, so the shorter duration, then the total energy is lower. So such trade-offs one can think of at the architectural level. Again, there is a need to manage the movement. So I just wanted to put up some of these optimization opportunities, indicating that such things are possible. Endurance is one thing we talked about, where leveling is where we try to balance the writing, because different parts, there is non-uniformity in the writing. Different parts of the memory, I might, they are not equally worn off. Some are worn out faster than others, and so that's what this is about, where leveling needs to be done. This is an understood phenomenon, was always done in flash memory, but in non-volatile caches this opportunity is there. And in fact, I would also like to highlight that some research, very interesting new research in this area is actually being done at IIT Guwahati. It's relevant because they are the people who are organizing this workshop, and it's nice to read about some of that very interesting work that they have done. Effectively, it could be that these in these caches, we restrict the writes to only some part of the memory, but not to all parts. And over a period of time, we, in some round robin or some other way, restrict, prevent the writes to different parts of the memory. That way you make sure that the writes are balanced in some ways. Reads, it does not matter, but writes, because they are expensive and they might lead to the system breaking down. Such things are there. So I just wanted to highlight that there are actually a lot of, there is very interesting work being done in this space in India also. So anyway, these are the kind of things that opportunities that are there at the high level. You can see the way the the innovation at the level of the devices translates into some high level picture and an optimization at the system level or an architecture level. Let's move on and talk a little bit about 3D memory. It consists of a stacking of DRAM dies. These are what are called through silicon vias. And we are stacking multiple dies to obtain a 3D structure. Why bother to do this? Well, first of all, it is good from a compactness point of view. Instead of spreading them out on a PCB, you have them just vertically aligned, and that's good. It's less volume. But it's also faster. The latency is lower. It's faster just because that path is faster than if it were to go out of the chip and through the PCB and so on. Bandwidth is higher because all of this, all of these that I have, right, these TSVs could go out simultaneously, and therefore many more pins can go out and connect into the processor. So in every sense, actually, there is a powerful advantage. For now, cost is high, and therefore there is some disadvantage. But of course, we're talking about a next generation memory. This has reached commercial products. In fact, companies like Samsung and SK Hynix are producing them. They're used in several products of the GPUs from NVIDIA, AMD, and some other accelerator products from Intel have been using it. Different kinds of stacking you can think of. You can have that CPU lying next to the DRAM. You could have the CPU stacked along with the DRAM. You could also have CPU and internal memory. CPU itself in several layers consisting of caches and so on, DRAM. So lots of possibilities here. Of course, all are not equally costly. Some are cheaper and some are more expensive. But that's the one separate silicon interposer and CPU memory separately. That's the one that is commercially used today. So those are the advantages, but in fact, there are some challenges here too. They ought to be there. But one that I want to point out is thermal issues, because you can see there is a difference in the power dissipation. There's a heat sink at the top. There's a PCB at the bottom, and leakage power is high. And therefore, you need to stall the temperature if that temperature, you need to stall the system if the temperature exceeds some threshold, otherwise it will break down. So here's what is happening. Heat flows into that heat sink. And what this animation is showing is initially everything is cool, but because of that gradation, dissipation is not so great from that layer. It is good from that top layer. What happens is that you see this thermal gradient. So in that direction, there's also that other possibility that the central channels are hotter. The central part of the dies become hotter than this peripheral. So these are just observations, and of course these ought to be taken as opportunities. So some work that we had done tried out this thing. You use backup as a normal 2D memory, that is the DDR. When things get hot, when some emergency level is reached, then you use a backup memory and turn off that channel. So channel turn off means that you are operating at a reduced level of performance, but that's still okay. It's better than shutting off that entire system. So when you turn the channels off, then you can see that there is these adjacent channels here. They begin to cool down. Those corner channels still remain hot, and maybe as the second step, you could move that data also outside. So you can think of some such management strategy for the data as a way to take advantage of this 3D memory structure. So on one hand, the compactness point of view is actually great, but on the other hand, from the overall management point of view, you see that it is not perfectly efficient because you need to worry about the temperature thresholds. There's some compromise, but that's still relatively okay. If you manage it well, then you can have a good and efficiently operating system. So yeah, this is just some examples of possibilities that show up here. And what I'm showing here is some work that we are involved in, where we are actually trying to build such a tool that actually integrates a number of things, the CPU performance, a thermal simulator, because that is what we need to do to analyze the temperature system. So some of these are open source tools that are already there. We are talking about open source here, which is an important theme in this in this program, and therefore I wanted to highlight that what we are putting up here together consists of all of these are open source tools, in fact. So all of these sniper, so these are different performance, but what is new is the integration of all of that, where you have maybe there is a processor that is running, there is an integrated DRAM set of layers, and I want to answer questions. I want to analyze, if I run these kind of workloads, if I run these kind of programs, what is the effect overall on the system, so that I can understand, I can actively intervene. And what kind of questions we can ask? We can come up with policies for thermal management. We can do scheduling of tasks. We could do maybe DVFS, voltage and frequency scaling. We could turn memory to low power mode and so on. Lots of things could be done. And what I wanted to point out is this is actually quite a bit of time we are spending here in making the tool usable. If somebody would like to try out these, let us know. And while this is still under construction right now, but what I showed previously, this is an example of a video that is the output. You run the system, and then that video tells you how, for example, the temperature profile has been changing with the time. So it's in the last stages, but we are excited to share it with anybody who is interested. This involves people on our side, and also other colleagues at University of Amsterdam and Karlsruhe Institute of Technology. As you might imagine, this is an integration of a number of different tools from different sources. Okay, so maybe I should summarize. We talked about emerging memory technologies and the fact that they open up a very new possibilities, lots of new challenges for everybody, right? From the process engineer to the VLSI engineer, to the circuit engineer, to the system designer and architect. In fact, all the way up to software, also a compiler, writer, operating system, and so on. Everybody is affected in some ways, and therefore they need to do something about it. We talked about non-volatile memory, where the capacity is high, there is on one side, but there are new properties of asymmetry and endurance that we need to do something about if you want efficiency in these systems. We talked about 3D memory, where there are some good things. Compactness is good, bandwidth is good, but also there are some very interesting new challenges that come up here. And of course, I want to point out that almost all the research that happens in this area is based on open source platforms, simulation platforms and modeling platform, and therefore they are all accessible to everybody. Even though we are talking, the technologies themselves are sophisticated, they are not even there in the market yet. Some of them are experimental, companies are trying out and are not there in product. Yet that does not prevent us from exploring this. That's actually the beauty of research. And it's not like it is expensive or something like that, because all of them are open source. And in fact, it's a simulation. We don't work directly with the devices because they are not there yet. But simulations tell us a lot about what's going on in systems like these and how to build efficient systems. So yeah, that was the talk. I would like to acknowledge the contributions of our PhD students and postdoc. Much of their work is what I have summarized here. The work that I talked about in the 3D memory, that's some of these students are actually working on this. And other areas that we are working on are this cache management, design automation, hardware accelerators, and AI accelerators. These are some of the works currently underway. I would also like to acknowledge sponsors of the work from the industry, Intel, NXP, Cadence, SRC, Semiconductor Research Corporation. Yeah, so these so this sort of summarizes the topic and also an acknowledgement to the people who are contributing to this. Of course, there are other colleagues at other institutions who are also involved. And through this process like this, if it happens that there is some synergy that is there, if somebody is interested or would like to work further in these areas, feel free to get in touch with us. We'll be happy to collaborate with many of these on these exciting next generation problems that come up. Thank you for listening. It was a pleasure to be involved. If there are any questions or comments, I'd be happy to take.
Hello.
Thank you, sir. Yeah. Thank you, sir.
Thank you very much, Professor Panda. Froja, are there any questions?
Yes, sir. There are a few questions in the Q&A section. So should I read the question?
Yeah, with permission of Professor Panda, we can do that.
Yes, sir.
Go ahead.
Yeah. Thank you, sir. Sir, why it is not possible to design the DRAM below 22 nanometer technology?
DRAM below 22 nanometer. Not that it is not possible. I'm sure that it is. Experimentally, different technologies are being tried out, but it is just that more efficient ones, since the technologists have found with more efficient technologies with respect to its resilience, its efficiency at the with respect to speed, and particularly with respect to the compactness, right, of those cells, density of these technology. It turns out that others are there. So it seems, of course, the DRAM 22 did not happen overnight. It represented an evolution that started long ago, and so DRAM is almost 50 years old now. It's maybe started from the 70s itself. So of course it would. It's hard to predict what the direction these are going. It is natural that other materials might come up, other circuit techniques would come up, and that is exactly what has happened here. Some technologies might plateau out at some geometries, and newer technologies might come up at different at lower geometries. So that's really what the situation is. DRAM is still being used. Of course, almost all memory. What we are talking about here is more experimental stuff and next generation stuff, and the density is what is the one of the primary attraction. DRAM, of course, remember there is that power related disadvantage is inherently there. DRAM means the power, because it's a capacitor, the power, the charge on the capacitor, of course, disappears over a period of time. That is just the nature of the capacitor. And non-volatile memory, the charge being retained even if you turn power off, is one of the advantages there that from a power point of view at least is important. So those are the reasons why they are considered attractive.
Thank you, sir. So the next question is, what is meant by memory coming close to CPU?
What's coming? Actually, an example of that we saw in the very first slide itself, if I can go back. Right. So in this picture, we saw there's a memory. The DRAM is the memory, right, for us, and the rest of it is essentially what is a modern CPU. CPU is not just the classical processor, but there's a graphics processor, there's an AI processor, there's cache, and so on together. But you see the DRAM here is actually in the same package. This, in fact, is an example of memory coming close to the CPU, coming physically close. This is not the extent to which it can come. The greatest extent is that, in fact, the two can be integrated in some ways in that memory. We can put some compute there. We will take part of that compute and actually move it over there. These are the in-memory computing technologies that are also being tried out. In some sense, they are physically coming closer. Physically coming closer is important, right? Otherwise, the thing is, we incur all that cost of the signal traveling all the way from there to here, which is bad for delay, it is bad for power, for energy, and so on. Why not? So if this processor, part of that computing circuit was actually located as close, right next to the bit cell, then you can see that much of that signal does not need to trace that long path. You have that data right there. and therefore your performance is better, your power is better, you can get a much better performance and much better power. So those are actually some of the directions in memory computing and near memory computing. This could be an example of a near memory computing where we are actually bringing it physically close, but still there is a demarcation between the processor part and the memory part. But we don't have to stop there, and new research of course is trying out newer technologies, newer ideas with respect to bringing them much closer. Yeah, so that's we didn't talk about it, but in fact that's the other part of the excitement with respect to research that involves memory and computation these days.
Thank you, sir. So the next question is again, will there be a movement of data internally between write-intensive memory and read-intensive memory?
Between yes, indeed, the data is going to be moving. We talked about that hybrid cache, and we said that in that hybrid cache there is part of it is write intensive and part of it is read intensive, but it doesn't work like that because in fact there are data which you subject to both the read and write operations, right? So it's just we are hoping to achieve that kind of a partitioning, but it is not going to be perfect. And in fact, data that you are writing now, maybe later on you will read, of course. So you need an active management policy here that would be moving data constantly back and forth. Hopefully it is not very frequently because if it is too frequent, then there is no particular advantage. But that's what that management algorithm has to be. We didn't talk about how that's going to be done, but clearly that needs to be done smartly, otherwise you'll lose the advantages.
Thank you, sir. Sir, the next question is, how is non-volatile memory more efficient in a long run?
How is it more efficient in the long run? Actually, if you look at this data, where does the efficiency come from? First of all, there is an area related efficiency, right? If you look at the extremes, this is almost like 100 times denser. That itself is a good enough reason. Now there are other things. So from a speed point of view, it is not so great, and of course people are still working on it. But why even consider, even forget about the fact it is non-volatile, but just the fact that it is denser is actually good reason for us to try those out and work out the consequences. It's not good, it's not perfect. If it were perfect, then in fact we would have moved long ago. So some of it is still experimental, but these are the reasons why they would be considered. Area is one, power is the other. All of these are low power, whereas SRAM and DRAM, they are all high power. So yeah, if area is this, and area, in terms of area it is good, in terms of power it is good, then obviously it's a good solution. It's just that a lot of other details are yet to be worked out. Speed has to be compromised and so on. So it's not perfect, but anyway, these are the reasons why you would be using them in the long run.
Thank you, sir. So the next question is, it is possible to design memories using CNT FET currently?
Yeah, so like I said, yeah, the CNT is carbon nanotubes. We did talk about a nanowire that DWM that we said was somewhere in that space. Essentially, it is a nanowire. So yes, these by no means are the only technologies. In fact, there's a lot more happening. Newer technologies are a very fertile area of research with respect to what the possibilities are, what the consequences are. So yeah, we didn't get a chance to go through all of them, but carbon nanotubes, quantum effects, these are all in fact hot with respect to newer possibilities. And if some of them turn out to be just from an engineering point of view, if some of them turn out to be practical and relatively inexpensive in the long run, then you can see that we are in for a big revolution with respect to design methodologies, with respect to architectural system design possibilities. All of them will come with some advantages and maybe other disadvantages also. And that's what keeps engineering alive. That's what keeps research alive. That's what essentially leads to that inexorable progress of technology and hopefully its benefit to mankind. So this is an open problem. What technologies are useful and what the future ones could be, who knows, there may be many. This is just the current stand. Some of it, we saw that through the discussion of the industrial adoption, there is to some extent there is an adoption, both of the non-volatile memory and the 3D, but the question really is open. A lot more still remains to be done.
Thank you, sir. Sir, we are having no more questions in the Q&A section. So may I request Professor Sahula, sir?
Yeah, I think it's my duty, present duty, to thank Professor Panda for his valuable time and enlightening us with so many aspects of memory architecture and its application and the scenarios, which were at least not known to me earlier. I think all participants would have been benefited. I am sure that way. Thank you, Professor Panda, for being with us, and we hope that you will be supporting us in future endeavors also. Thank you very much for your.
Absolutely. Yes. Yeah. Thanks a lot again, Professor Saula. It was a pleasure to be here, and thank you for your invitation. It's great to have this audience, and the questions were also very appropriate. And wish you all the best for the rest of the workshop.
Thank you. Thank you, sir. Thank you, sir.
Thank you, sir. We have an important announcement for all the participants. Now we will be having a 5 minutes break and we will start immediately. I request all the participants to please note that we have shared the link for joining this event to your respective registered email ID. So I request you all to please check your all mail folder to get the link for the event. We also request you all to please join the event by using your registered email ID, because that email ID will be used as a tracker for marking the attendance, and attendance is very much required. So we request you to please note the same. We have also shared with you all the drive link. In the drive link, we are having the important one folder where the important announcements are being given. So we request you all to please keep on visiting the important announcement page for all the course related announcements. We request all the participants to take a break of 5 minutes. We will start the event at 11:34. Thank you. Good morning, Aditya sir. Aditya sir, good morning.
Yes, ma'am. Sorry.
Yeah, good morning, sir. So we have given you the presenter, right? So you can just check if once if it is working fine.
Okay, here.
So the slides are visible, sir.
Perfect. I think it's the wrong view. This should fix. No, this one. Let me change the screen. Give me one moment.
Okay, sure, sir.
Okay, I hope you are able to see the screen.
Yes, sir. We can see your slides, sir.
Perfect. Yeah, I think we are running late by half an hour. So yeah, I'll split my talk into two. I'll cover some section right now. It is also important to cover some aspects after Puneet's talk. So I'll put some aspect of it at the end of today's session. So
Okay, sure,
that
sir.
ways it is better for the participants to follow along and they know what they want to do before coming to the next session also.
Okay, sure, sir. So we have given a break till 11:30.
Yeah, I know. I was just talking to you about how
Yes,
we
sir.
need
Yes,
to.
sir.
Yeah.
Yes, sir. So just 1 minute left,
Yeah,
sir.
yeah.
So we will start sharp so that we can cover up the timing.
Sure.
Okay. Thank you, sir. So good morning, dear participant and our experts. So we are starting with the second session for day one. The second session for day one is going to be delivered by Dr. Aditya Dalakoti. Dr. Aditya Dalakoti did his BTech in Electrical Engineering from Indian Institute of Technology, Ropar. Following this, he did his master's and PhD in Mixed Signal Circuit Design from University of California. Following this, he has been involved in research and development division of the Continental in both USA and India. He has also been an active honorary advisor for multiple educational organizations like TechnoRead and VLSI Expert. So with this, on behalf of all the Electronics and ICT Academy, we would like to invite Aditya sir to please start with the session. Sir, may we request you to please.
Hello. Thank you, ma'am. Thank you for the introduction. Thank you everyone for all the participants who joined this program, and thank you for Professor Panda for that wonderful lecture. It was quite insightful. The overall goal of the session today is there is a session right now, and then there is a session by Puneet later on, is to give you an introduction on what we want to do with the course, what we want to achieve with this course. In that regards, what I'll do is first I'll go over the general agenda, which day we'll do what, and what are the general expectations right now. Then Puneet will go with the general aspects of why we are doing this course. And then at the end, we'll cover some of the installations requirements needed to be done to follow along better for the rest of the 9 days of the course. So the rest of the 9 days are going to be quite hands-on design work. You'll be actively working in the tools to get GDS ready. So because we'll be doing that, it is important for you to have a look in the background in terms of what all software installations you should have. So because it creates a bandwidth limitation, I'll get my video off for a bit, and then I'll switch it on later at the Q&A and stuff. Okay. So now moving along, as I mentioned, basically, what do we want to achieve out of this program of today and then the rest following 9 days? Of course, there are really great and insightful talks by a lot of keynote speakers who will give you a bigger perspective on the architecture and design front on how do you take the existing open source infrastructure and augment that with a lot of research of your own, a lot of design work of your own. Our agenda with respect to this specific course is to take a parallel line on that, and we want to explore, now that you have, if suppose there are existing IPs there which are free and open source, and there are existing, you want to do research on them, you want to do design work on them, how do you evaluate them? And also how does the whole flow to actually make a complete GDS work? So we wanted to give you a perspective of that so that you can take everything in open source and use that to your advantage and make something real out of it. This is also important from another perspective. I've been in the academic publishing world for a long time now. And what I've realized is a lot of times publications from not top tier universities in India do not make the cut of good journals because a lot of time data with they have like standards where if you do not publish the final GDS results, final simulation results post PNR, or if you do not try to simulate or present the data in multiple technologies with real physical implementations, they do not even accept your work. Now with the advent of so many open source tools out there, and the fact that you have these PDKs available online to you, you should be able to run them on your own, in your own research for different technology evaluations, even for taking the research to product development from your own labs. So that this is one step in enabling such endeavors from different academic institutions and different industrial institutions to take such efforts forward, so that we are able to actually make products out of our research and also be able to present our research better to the community over the world. So that is the general motivation behind this program. In order to do this, what we have taken, we'll be taking few open source RISC cores which are available in the freely, and we'll be trying to see how do we visualize them, how do we what do we mean by RISC compliant. There are repos out there, we'll show you what can you run against. Then the major part of the goal is to actually take another route. We want to take now these multiple cores, we'll run one, we'll make you run one. So it is not you'll be exactly copying our work, you will be supposed to actually run a core in parallel on your own and fix the issues on your own and interact in real time and ask us questions. Okay, if we are facing this, what do we do? So that's the general agenda, that you will be owning a core and you'll try to run it on your own. Now, if everything is anyone who is a little bit familiar with the RTL2GDS world would be like, if the scripts are set up, we can just press a button and run it. And if you have ever run the open source environment, you'll say the same question. Well, we can just press the button and run it. The question is not to be able to run it. The question is to be able to run, to understand what is happening in those scripts, each step, each thing, and to be able to modify them. Because when you implement such things in real time in your own applications, there'll be no one who has actually set up this magic script for you. You will be the one who will need to modify those scripts. You will be the one who needs to know what is going on in them. And that will be you who will be responsible for setting that up completely. So that is The motivation behind them to give the power to you to be able to run and present your work, to make products out of your work with the open source environment already in the available freely now. And RISC-V being the major part of and with the growth it has seen over the years. So now what we'll start with this program is showing some simulations and characterization. We have taken the help of CPP sim tool here, plus we'll show some GitHub repos on risk compliance on this. Basically, we'll show you the overall, what do you mean when we say simulate a core, simulate an RTL2GDS, we want to show that. Plus, there are a lot of files which are associated in the RTL2GDS flow, which are generated out of simulations. And when people run those RTL2GDS files, people are not aware, okay, where did we actually get this? Why are we seeing this effect? So we wanted to set up a simulation environment for you so that you are able to model, see those effects, and if needed, also simulate to also visualize how do you counter those effects. So that's why we wanted to start this program with the simulation and characterization based on the CPP sim framework. Then we'll talk a little bit about basic timing constraints and synthesis. And with respect to this, we'll take the help of EOSys tool, and in the tool we'll observe what basic synthesis mean, how can you specify simple timing constraints, and that will lead to some timing analysis later using OpenSTA. We'll take a little bit of deep dive into some of the input-output files which are needed in the overall RTL2GDS flow. We'll talk about layer and power planning. We'll also think about how nowadays a lot of talk is about low power aspects in the layer and power planning aspect design. There is a lot of talk about low power design. How can you make your cores low power? We'll talk about that. How can you make your SoC low power? We'll talk about that a little bit. Then we'll also be overviewing how do you do complete STA for such things, for such cores. Then we'll follow that along with floor planning, placement, clock tree synthesis, routing, and sign off. So, and then we'll come back from the sign off and we'll visualize how do we take the final netlist and what does it mean to do a final check off simulation on it. So this is, and we'll take a core, you'll take a core, we'll both work in parallel and try to achieve a final GDS out of it. Now, the way the program has been structured, there are specific topics to be targeted in every day, but we are going to keep it a little bit flexible. If we, the overall goal is to achieve multiple GDS, PNR, complete GDS flow for RISC-V cores on our side, on your side. And if there are a lot of active interactions, it is not necessary that we cover everything assigned for that day on that specific day. We can, there is a lot of freedom and moving around these things. So please feel free to interact as much as possible. In the next few slides, I will only present the general agenda for the next few days, what we want to target and what we want to cover with respect to the RTL2GDS flow. But we have a lot of freedom in moving around the things. Okay, we can do this a little bit later, or we have time freedom as well. Please, the course, the tutorial has been designed to make it as interactive as possible. You need to be ask as much as possible, so that, as I mentioned, you need to understand it well to be able to implement something new on your own. So that's the general perspective. I'll quickly give you a general overview of the agenda and program for the next 10 days, today and the next 9 days. So we'll have an introduction on the topic, why we are doing what we are doing, and topics like those in the session by Puneet today. Then we are going to have this is the program overview. What are the general expectations from the participants? One thing I would like to add here is that because we'll be requesting you to follow along and run the RTL2GDS flow for your own core, there are 2 quizzes which are being assigned on Thursdays if you look at the program schedule. So a part of the requirement of the quiz can be that we might ask you to upload a file. We are based on what kind of participation interaction we get from the participants. We may put different requirements there into. Okay, upload just the snapshots of this in terms of file upload in the quiz link itself. So we'll see how that goes, and that depends on how the interaction with the participants is happening as well. So after Puneet's session, what we'll do is we'll look at the installation requirements, what all you should have. Some of these things we can also install live during the next sessions, but I'll give you an overview in the end of the day today. The general idea is you should know that you need to have a machine compatible to be installing such things. We can do them live. We will also set them up live in the next sessions, from Tuesday's sessions. But just to give you an overview of what is needed. CPP sim in particular, I expect everyone to have beforehand installed. Otherwise, it will take a lot of time to get that up and running. Okay. So what I'll do is I'll go through all the training agenda for the day, and then at the end I'll come back and see if I have any questions on this. And then also at the end of the day today, obviously I'll come back and go over with the installation aspect, so you can ask me questions then also. Okay, and as I mentioned, then on the next day too, we'll have the simulations and characterization aspects on how do we do the base, what are all the different simulations necessary if you are designing something, what are the different characterization aspects, how do you do library generations. Then there'll be a session by Puneet where he goes over circuits, architectures and systems or from the low power perspective, because a lot of these cores nowadays, there is an emphasis on how do you make them low power. So you have a RISC-V core, which obviously you can scale in technology, but what all can you do and exploring different techniques from circuits, architecture and systems to make such things low power for say IoT applications. We'll have a session on that. Then we'll have sessions on constraints and synthesis. On the day 3, we'll start exploring synthesis using YOSYS. We'll have general IO files discussion. Following that, we'll have some SOC perspective on constraints on the next day, and then we'll quickly run some synthesis on RISC-V cores. And then we'll have a little bit of detailed discussion on lib files with respect to the IO files. You need to understand a large part of this course is giving you very fundamental basics of the RTL2GDS and not going into very in-depth complex methodology. The reason for the fundamental basics is because with the open source environment, if you know the fundamental, you can modify as and what is needed to suit your own research, to suit your own product development. It is to give you the power. If you know the basics, you can do the rest. That is the general aim. Then on day 5, we'll dive into the layer and power planning from system planning and layer power planning open lane tool for power distribution networks. And we'll start the first dive into the static timing analysis with respect to delay calculations. On the next following week, we'll start diving into the PNR aspects with respect to the floor planning and have a setup and hold discussion on the STF front. From the next day, we'll have the placement and again, STA reports and analysis and the following day, we'll have CTS and again, more STA on the complex techniques overview. So the reason I'm moving a little bit fast along here is because a lot of these things are the general overall goals of this program. There, as I mentioned, based on how much you interact, how much we try to figure out things together, there is a lot of leeway on what do we do when we can move around things. So please make it interactive. Let's try to learn this open lane environment, the open source environment, and try to do as much as possible with the RISC-V cores. Let's explore them as much as possible with these open source environments together. That should be the overall achievement out of this course. Then at the end, we'll go over the routing techniques, routing basics, and we'll also look into what is the DRC LVS extraction concepts, and we'll do on the tool as well. Then at the end of the agenda is we'll go over what are the industry methods on achieving some low power designs. There is also a keynote on this. We expected, I think, which is scheduled to be, I'll need to check. Yeah, I think by Mr. Gaurav, we have an excellent keynote on this, which is expected. And then we'll do some designs final sign-off checks aspect on the last day. So this is the general agenda. Of these slides will be uploaded, and the next following slides regarding the installation, I'll come back to towards the end of the day. That is, it is better to align it that way, because then it is, you know what you're targeting. So now I'll try to see if there are any questions. Okay. Obviously, you can ask questions to the end of the program. Okay. So Mahesh, what should be installed before I'll get back to towards the end of this today's session? After Puneet's session, we'll have we'll split the session into two, and I'll cover that up. The GitHub repository, Neeraj, for sure. We will be sharing some installation links. We'll be putting the slide deck online. We will also share which GitHub repos we will be using. So all that will be shared, plus the design, some examples to visualize, say, synthesis methods, where those examples will upload online as well. So everything will be available to you online for sure. And with respect to Mahesh's question, and probably a lot of other people's question, with what do we need to install, how do we need to install, when do we need to install, we'll come back. You do not need to own any RTL code. We'll let you know which RTL code to use, and where do you pull it from. We'll let you know all that. Surya, let's wait and come back at the end of this session. There are multiple installations. There is not just a single one, because we want to cover the whole design suite aspect rather than just one thing. So there, since it is better, we cover it together at the end. I mean, for sure, you can run your own code. That is what the aim of the course is, to enable you to do that. You can run whatever you want. You can visualize whatever you want. That is the goal, to give you the power to run this. Obviously, no one's stopping you from running your own codes. Sure, it's fine. You can test those as well. That's the reason for having this program, so that you're able to visualize all your own designs. But we would request you to have do the RISC-V codes we provide you as well, because that will give you a lot more understanding. So let's get, I'll answer there are mostly tickle scripts, Rajesh, Asif, Ubuntu latest version on a VirtualBox is fine. There is a slightly older version that is fine as well. I don't think there is a specific blocking point with respect to Ubuntu. Naveen, we can come back to your question on when we talk about synthesis constraints, and we can discuss a little bit about virtual clocks then. We have the input output constraints there, and I think we'll be able to figure that out then. It's fine. It's part of the program. Okay, so this is good. The prerequisite for the course is you should have some basic knowledge of CMOS, and pretty much it. And you should be able to run simple Linux commands. So apart from that, I think we want to take it slow, and anyone has any doubts, please feel free to ask. No one is expected to be an expert in anything here on all the topics. The agenda is to take it very slow and basic, and enable everyone to learn all this so that you're able to use it. So if you know basic CMOS and digital, it should be fine. No, open source softwares on Windows is not possible. Please install VirtualBox on your Windows and installing Ubuntu in it if possible, or any other Linux distribution you like. Front-end verification is another aspect which we will be tackling in later. This is not part, Puneet will actually dive into that, the general aspects we are trying to cater with this course. Front end we will have in a parallel course later on with and Gaurav sir has planned that already in later aspects. Currently the idea is for you to visualize things first and then dive into more front end development later, so that you have this already in your beginning. Naveen, the next class is on Tuesday, and a lot, so don't worry, you'll have enough time to install things on your own. And we will be uploading the installation requirements in the drive today itself. So there is Sunday, there is Monday, so you'll have enough time. I'm not sure, Mr. Shankar, if with respect to bank. You'll need to so obviously CPP SIM, yes, you can. VirtualBox, sure, Nitin, we'll be providing guide on what to do, how to install tools in our in Ubuntu, yes. Okay, I think most of these questions are with respect to installation. We'll come back to these anyway at the end. So Firoza ma'am, I think we are good to go for the keynote by Professor Balakrishnan.
Okay, sure. Thank you, sir. Thank you.
I'll stop sharing. Okay, perfect. Thanks, everyone. I'll come back to you at the end of the today's session now.
Thank you, sir. Yeah, thank you, sir.
Yeah, Dr. Firoja.
Yes, sir.
It seems Professor Balakrishnan sir has not joined.
Yes, sir. Yes, sir. We are just trying to track.
Number. I think all mobile numbers of his has changed. I'm trying all numbers. Give me 5 minutes.
Okay. Okay, so just we can give 2 minutes of break. In the meantime, we will be connecting, sir, if possible. Hello, sir.
I think it's better to have a 5-minute break possible.
Okay, sure. Okay. With your permission, sir, I request all the participants to take 5 minutes of break. In the meantime, we will make all the necessary settings and we will start. So we will start at 12:05. So we request all the participants to please stay connected and take a 5 minutes break. Thank you, sir.
Dr. Firoja.
Yes, sir. Good afternoon, sir. Yes, sir.
Yeah, I'm Vineet here. I'm just leaving for 5 minutes to contact him on the Teams. He might be online there.
Okay. Sure, sir. Sure, sir. Yeah. Okay. Thank you, sir. Dear participant, we request you all to please note that we will be considering the attendance based on the registered email ID. So we request you all to please connect by your registered email ID. We are getting a lot of requests regarding the pre-recorded lectures. So we request you all to please note that in the YouTube channel of E&ICT Academy IIT Guwahati, these lectures will be available. But those lectures are only for reference and for your study purpose. This will the people who will be joining the YouTube link will not be considered as an attendance. So I request you all to please use the YouTube link for the study purpose only. Other you have to connect us through your registered email ID in the WebEx event only. We are having few delay in the session. We are trying to contact our expert. So we request you to please bear with us. Apology from our end. We will be starting in few minutes. Thank you.
Firoza ma'am.
Yes, sir.
So if we get delay, then maybe what I can do, I can just start my session. Maybe once the sir will come, then we can
Yes,
do
sir.
in
We
that
are
way.
planning for the same, sir. So can you just give me 1 more minute, sir? I'm getting the confirmation and then I will inform.
Yes,
Just
yes,
1
please.
minute. Sir. Okay. Thank you, sir. Yes, sir, Puneet, sir. So just give me 2 more minutes. I had a word with Gaurav, sir. So Gaurav, sir will confirm me and I will inform you, sir.
No issue.
Thank you, sir. Good morning, Puneet sir. So I think so we can start with the session. There is some urgent issues, as a result of which sir could not join. So sir will be joining in the subsequent coming session.
Okay, no problem.
So sir, just 1 second, sir. We are making all the necessary setting. To please give the presenter right to Puneet sir. Sir, we have given you the presenter, right? So may we request you to please check. Yeah. So your video is coming properly. Thank you, Aditi. So, sir, can we just, can you share the slide? We can just check once.
Yes. I'm just trying. Sure you can see it.
Yes, sir. We can see the slide, sir.
Okay, great.
Okay, so on behalf of E&ICT Academy, we apology to all the participants that we cannot have the keynote session 2 for today's session. So we will be scheduling it in the subsequent sessions. So apology from our end, and we will be starting the 3rd session for day 1. So we, on behalf of all the Electronics and ICT Academy, we would like to invite Mr. Puneet Mittal, sir. Mr. Puneet Mittal, sir, is the founder of VLSI Expert Private Limited. He holds a BE degree in Electrical and Electronics from COER, ME Communication System from BITS Pilani, and MBA from Symbiosis Pune. He comes with a rich experience of 14 years in embedded and semiconductor industry, and has also worked with biggest organization in the VLSI industry like Cadence, Synopsys, Magma, and LIC Logic. In VLSI field, Puneet sir's key expertise are in static time analysis, PR flow, method development with leading industry tools like from Synopsys, Cadence, and Mentor. Proficient in handling team mentoring, project management, customer engagement. Puneet sir has also been working in the last 10 years in bridging the gap between the industry and the academia with the help of seminar, workshops, and skill development program, and also as a guest lecturer. He is also doing a consultancy education sector from school level to university level in terms of designing curriculum, training faculties, infrastructure building, advanced learning techniques with technology. He has also been instrumented in skill development in VLSI domain for almost a decade through a dedicated online portal. He has created an online expert group, a VLSI expert group in the semiconductor field, through which he is interacting with several students, educational institutes, and university. He is also associated with several social professional societies which are in education sector like Youth Career Counseling and Employment Bureau, the Indo-Canadian Innovation and the Skill Development Center. He also loved doing the career counseling and mentoring for the students. So with this brief profile, we would like to invite Puneet sir to please start with the session. May we, sir?
Yes, thank you, Firoza ma'am. Thank you, everyone. So I think all of you guys
Thank you, sir.
All of you guys are able to see my screen properly, and Aditya shared with you last time, like session should be interactive as much as possible. So maybe today's session, maybe you may be thinking like, okay, what exactly you can ask, and I know there are a couple of questions maybe you have in your mind. So the next half an hour, I will just try to keep it as short as possible, and next half an hour we'll just try just to answer few of the questions which maybe you have right now in your mind. Like let's start with the very basic thing. Like all of us were talking about the RISC-V, all of us we are talking about the RISC-V implementation flow. We were talking about this buzzword, and then we were talking about the open source community, open source tools, open source, everything is open source we are talking about. So I just try to give you the couple of aspect from the open source, from the RISC-V basically RISC-V perspective, and after that I will just give you an idea about why we came up with this particular topic, what are the different areas where you can work, and like Aditya also mentioned, like what we are going to cover and what we are not going to cover here. Apart from that, when it comes to what is the scope of uh, uh, this particular workshop, if I will say in that particular thing. And then in the last, I will come up with a very quick RTL2GDS flow. I will just give you that particular idea because that's a backbone of the whole workshop. And maybe you may be thinking like, okay, I'm running in some places and some slides, so that's okay. Like Firuza ma'am already mentioned, you will get everything on a YouTube, so you can just later on you can pause it, slow down the speed also. So YouTube have a very good feature. You can increase the speed also, you can decrease the speed also. So you can just do that particular part, and you can start uh, uh, those things. So coming back to the topic, it is like the RISC-V. So you can see, I think most of my slides are self-explanatory, but still I will just give you an idea. So if you will see this particular slide, this particular the 2015 Q3 to 2019 the RISC-V. So this is basically one of the snapshot which I have captured from RISC-V Foundation, and this is a basically the growth they were talking about between the 15 and 19. Last year growth, uh, either it wasn't available there or I didn't check it that particular part. But yes, so you can see like the way this particular RISC-V community, the members, the adoption, the way it is increasing day by day. So you can see like, okay, there are semiconductor IPs, if you will see from the last one, like 45 semiconductor IPs. So you can see with the help of this, we are also talking about the IPs. We are talking about the different areas, like we were talking about the machine learning. We were talking about the networking. We were talking about the developers also. We are talking about the tools. So what we have done, not we, basically this RISC-V community, what they have done when in terms of the consultancy companies, and then in terms of the universities, the adoption, how many people have adopted the RISC-V. So it's like from the adoption point of view, it is increasing day by day, and we as a Indian, if you will say, and as a industry people, if you will ask, we are also trying to play some role in this particular contribution. This particular workshop is more or less just to give an idea, like, okay, with this RISC-V, what all different things you can do, and if let us suppose if you want to build your own product, can you do that particular part? So that's the goal of our whole workshop. Just to give you an idea about the open source community in terms of the hardware and software. The software, most of the people know very well. Most of the companies, most of the, at least when I'm going to talk about the educational institute, when I'm talking about the students, when I'm talking about the research scholar, so we know about the open source software. We know all these things are open source, and we are most of the thing we are using day in day out, and maybe we don't know where these are the open source thing. So like for example, just a couple of minutes back, Aditya mentioned Ubuntu. Like, okay, we have to install the Ubuntu. Now that is also a open source software, the Linux, Unix, when we were talking about that particular thing. So it started with the open source, from the open source community, by the open source community. So that portion we are clear. Now when we are talking about the hardware, so there are a lot of people still, they have a doubt, like, okay, what is the open source hardware? How can a open source hardware can be a successful thing? So this particular slide, just to give you an idea, like, okay, it's not when the software can be in that particular zone, like where today we don't know that, okay, these are the open source, then why can't we just focus on the open source hardware also? So RISC-V is one of the key player when it comes to the open source hardware point of view. People usually talk about, like, okay, if we are talking about the RISC-V based processor, then uh, does that mean it's going to be the low performance? Because we as a human, we have this some notion, I would say, like, okay, if it is a open source, if it is free of course, I would say the free and the open source, then maybe it is not as that good as a commercial high paying thing. So this is again not my comparison, just I'm iterating again that, okay, there are a few areas where you can ask me, like, okay, how this thing. So this is one of the comparison done by the hot chip in 2017 USB UCB. So they did this comparison on the RISC-V rocket and the ARM Cortex-A5, and they were just talking about this particular part, and they just mentioned, like, okay, it's not only from the architecture point of view or the ISA point of view, everywhere if you will see. So it is comparable. Like, okay, even we can go with the process TSMC 40G that both in the RISC-V also in the ARM Cortex also. And remember, this particular comparison, I'm just talking just 3 year before. So just to give you an idea, like, okay, if you have something in your mind and if you want to design it, if you want to play around that particular part, so don't think like, okay, if you have to go commercially, then you need a commercial processor, commercial tool. That's not the that's not the thing. You can go with the open source, or you can go with the free tools also. And I like in the starting itself, Gaurav sir mentioned, and the Shakti processor which we were talking about. So that's the best example. Like, okay, we can do a lot of things. We can come up with the products also. Now, when it comes to the computer system, now I just want to give you an idea uh, from the engineer point of view. Now, as a layman language, if I want to give an idea, like, okay, what is everything? So for you, basically, you have a problem statement. So you will come, and this should be your flow, I would say, but you have to understand a couple of things. So let us suppose you have a problem statement. So what exactly you're going to do, and that how the computer, the software, and the hardware, where those things come into the picture. For example, now you just want to add two numbers. So first you have to come up with a certain algorithm. Like, okay, this is the algorithm. Now, what is the algorithm? A lot of people, at least in the engineering and software field, they think like, okay, algorithm is a it's just like some rocket science. It's basically, if you will ask me as an engineer, for me, it's just like your approach, like how you're going to design it, how you're going to code it, how you're going to optimize it. All those things as a part of your algorithm. So two number, perform addition, store in the display, then this become your algorithm. Then you're going to have a program. Maybe it is based on the C program, Java program, and maybe some other language, any language. Forget about the language, but I'm just talking about that you have a program. And in that particular program, now till now, as a user, as a front-end user, like I'm sitting in front of a computer, and if I want to have a problem, then what exactly I'm going to do? So the first three block is basically from that particular thing. Like, okay, you're going to write, you have a problem, you're going to have some algorithm or the approach, and then on the basis of that, you're using a particular program, you're going to write something. Now, what is this instruction set architecture? Now, let's talk about, this is something related to, I'm talking about again from the hardware point of view. So now from the machine, try to understand from the machine perspectives. I mean, I'm seeing the machine, I'm seeing the hardware, how hardware is going to understand. So for that, you should have something which hardware can understand. And now obviously hardware is right now, if I will say how the hardware can understand. Obviously, you have to design a hardware in such a way like, okay, it can understand. So if you will design a hardware, it can understand. So as a human being, uh, uh, hardware don't have a brain as such. The way we are going to design it, the way the language, we will say, it will understand that particular language. So the instruction set is a something like we are tuning our hardware. We are saying like, okay, this is the chip or maybe the registers or the transistors, whatever we are talking about. So using this instruction set and whatever the architecture we are talking about, we are just making sure like, okay, my program should able to understand by that particular hardware. So this place where you may be thinking like, okay, what, how it is going to be happen, this is basically a human readable program, and it is going to be translated to represent the computer can understand. That's basically is this particular place. Now once that is done, then in a maybe you may be thinking like, okay, how does a modern computer execute that particular program? So we will not talk about, but that goes in a one direction, like, micro architecture, and then we will talk about the circuit. So this is basically the whole flow. So as a human being, if you're sitting in next to your laptop or the computer, and if you want to solve a particular problem, so most of the software engineers, they usually work on this particular side. These three blocks basically, they usually work on the top three blocks. Now from here, basically this instruction set architecture. Now the question come, who is going to design these instruction set, ISA? So who's going to design this particular part? Because on the basis of that, the hardware we are going to design, and then once this is done, if then the circuit come into the picture. Now the RISC-V, when we are talking about the RISC-V, so this is the area where it is very important for all of us to understand. I was talking about the translation and the compilation. So this is, let us suppose, your language. So if you will see, this is something, maybe you can see like, okay, int a equals to b, int b equals to 2, int c equals to a plus b. This is that sum of 2. And this is something in a C language, and you can read it and you can understand this particular part. But with the help of the eyes, the way I'm able to read it, hardware cannot read this particular part. So what we have to do, we have to translate and we have to compile and we have to come up with some binary thing. Now when we are talking about the binary, all of us know very well. So if we are from the electronics background, we know our hardware can understand 0 1. Now what is the 0 1? Again, that is not a exactly, you will say like, okay, if I will write somewhere as a 0, it can understand the 0, and if I will write somewhere as a 1, it can understand 1. It is basically again, as a human, we define within our hardware like, okay, from the voltage point of view, below this, that is 1, sorry, below this, that is 0, and above this particular voltage, it is 1 again. So that means now we are linking everything with the voltages, and then as a that particular reference, that particular line, the way you are going to design the circuit, that is basically define the 0 and 1. So Aditya mentioned like, okay, you should have a basic understanding about the CMOS portion. So that's again the different story, like, okay, different area where you can go back and you can just check like, okay, what is the meaning of a 0 1, how you can define all these reference, like uh, uh, is with respect to the VT, the threshold voltage, or now then there is a one more field like 0 1, if we are talking about, that is the digital one or the analog one. So analog field, digital field, and then the mixed signal, all those things come into the picture. So that particular portion is basically in terms of this machine readable thing, and now how you're going to write, how you're going to compile it, how you're going to talk about this particular data. Now the question come from this human readable language to the machine readable, how these things is going to be happen. So it's not like you are writing a program and once you will write a program, it will automatically convert. That automatically, that means there should be something between these two things. Now for that particular part, there is going to be some executable binary. I would say just between this, there should be something which is I'm talking about. That's some portion, some language, and in that particular language, once your human readable program will go, it will reach to the next level. So if you will see this opcode based program, so what is this opcode based program? So with the help of some program, maybe maybe you can say like, okay, some software or something. So like here, I'm just talking about the assembler. With the help of the assembler, you're going to convert it into in this particular fashion. And this fashion, this thing, whatever we have written here, like an opcode based program, now this is going to be executable, and this is with respect to the particular instruction which are stored into the memory. So now think, I'm not from the hardware point of view, I'm not telling you anything like anything which is going to be happen automatically. Now I'm saying like, okay, there is something is stored into the memory. So stored into the memory, Panda sir, he mentioned like, okay, the importance of the memory we are talking about. So now if you have a very complex system, the very complex architecture, then definitely you have to store in that particular memory some instruction sets. So if you know like, okay, in our computer, in our laptop, in our processor, when we have all these things, the hardware things, there is a portion of the memory which you cannot write on that particular portion of the memory, because that is the internal memory. Now what is the meaning of the internal, or something is written there, that is this particular part. So what happened, there is a piece of a table or some memory is going to be there, and all these opcodes are stored there, all those is written. So in language we usually talk about like the syntax. Similarly there also it is sort of syntax, I would say, in the hardware things. So those things are written. Now if these are matching, and as per this, the things are going to be happen. So and that particular portion, it is written like, okay, what next supposed to be done. So like move L, and some dollar is some variable is going to be there, and some variable is going to be there. So these are basically the numbers or the memory location or something. So these are basically the memory locations, like some data is stored in this particular place. So the moment in a hardware that program, once this thing will go, the moment it will go, it will just store in that particular memory. And accordingly, we are saying like, okay, the processor read these instructions from the memory, because it is stored in the memory, and execute instruction one by one. So the moment you will say execute, it will execute it, and then it will convert into the executable binary. So that's basically I was just talking about from the instruction set architecture. So the reason I'm just trying to give you like, okay, what is the instruction set architecture? Yes, it is a uh, separate topic. It is a big topic also. Like, okay, there is this separate course also. Like, okay, how we are going to write the instruction set instruction sets, and if you have to write it, so you can how you're going to write your own ISA. And even in the case of RISC-V, if you want to do something, then what are their predefined ISA. So I will just give you one small thing like, okay, how many instructions set the RISC-V can take it. So basically, it's all about the uh, a a particular processor, what all different things it can do, or the compatible to do all those things. So this is the importance of the ISA. Now, this was something which I was talking about from the computer, like, okay, If it is your memory, then there are the instructions, and this is dedicated to those instructions which I was just talking about the previous slide. And here basically if you are talking about the processor, so there is a control, program counter, registers. So the way from the memory, the way they are going to and fro the things, it is basically the whole computer I'm talking about. Now the question comes, why I was talking about the instruction set, why all of you guys should be able to understand, like, okay, what is the instruction set? Why uh, I just mentioned, like, okay, you can write your own instruction set also. What is the need of a new instruction set? So why there is any need of a new instruction set? It's a very simple, like, okay, so so think in this way, there are two ways. Someone else is going to write an instruction set for you, and you are going to reuse that particular instruction set. And if as a businessman, if I'm going to write an instruction set for you, and if I'm providing you the support of that particular instruction set, and I'm saying, like, okay, if you're going to follow these instruction set, that means it's not only the instruction set, I'm also talking about the hardware. I'm also talking about, like, because that particular portion of the hardware is going to be is going to work only and only when it is going to follow a particular instruction set. So that means if I have designed for you as a businessman, then I want to generate a revenue from that. So when I have used a word a couple of slides back, like, okay, the open source, and I was talking about the I'm going to show you one more thing, like, okay, in terms of the commercial thing. So if I'm making a money out of that, then that becomes the commercial portion. Now, if I'm just giving you the freedom, like, okay, you can write, you can design, you can do anything out of that. That means now we are talking about the open source. Now there is a third thing, which is a free. That the free in the sense you cannot make the changes, but it's free of cost. I'm not going to charge from you. I'm not saying, like, okay, if you're going to use this particular thing, then you have to pay this much as a loyalty, or you have to just or give me some money. So there are three different terminology right now we are using in the industry: the commercial, where you have to pay money; the open source, where you can also make changes and you can also contribute for others; and the third is a free. That means you can use it, but you cannot make changes. So if as a research scholars, as a university, if as a student, if I will talk about, so what is your end goal? Let's try to understand in that particular way. The first thing is the research. Now, if we are going to take a predefined or restricted, or I would say something which where you cannot make any changes, then you have a limitation in terms of the research. So you cannot do any research there, because at least in not in that particular domain. So you have to use it, and you have to just use it as it is. So a lot of people, they came back in a last several year, like, okay, we have a industry standard commercial tools. Can we change? Can we add this functionality? No. So for that, you have to go back and you have to just check that particular vendor. I need this particular uh, functionality. There are a lot of people, they were asking, like, okay, we want to design a new tool, and or maybe the existing tool, we want to make these changes, but you cannot make those changes even though if you are as a researcher, because maybe that particular feature is not available in that particular tool. So similarly, on a hardware side, if you want to do something, you cannot do that particular thing because that is already defined by someone else. So that's the reason I'm talking about the new instruction set, or the new thing I'm talking about. Another thing is, as a research scholars, as a university people, sometimes we don't need a complex hardware. We don't need anything very complex, because we just want to try 2 plus 2. That's all. You want to play with a 2 plus 2 equals to 4. Maybe you want to prove it, like, okay, can it's possible with this particular approach that 2 plus 2 equals to 5? Maybe. So if you are thinking in that particular way, which is a good thought process, but you have to prove it, like, okay, 2 plus 2 equals to, it can be 5 also. Maybe you will come up and you will say, like, okay, from the voltage point of view, these are the threshold values, VT and the VT, as per, I'm just converting this particular numeric to into a voltages as per our the CMOS VT. Now it becomes 0 1 0 1 something, and then you are just adding that particular part, and tomorrow you are coming up with those particular voltage and is saying, like, okay, now it become 5. Maybe it is coming 4 point more than 4.67 volt, and then you are saying, like, okay, now the threshold voltage is defined in such a way it is equivalent to the 5. I'm taking an example because everything is based on the voltage and the reference which you're talking about. So I still remember, like, just a couple of weeks back, there was one more FDP, and Ashish from DRDO, he was just hosting that particular FDP, and he also mentioned in a similar fashion, if you are saying 2 plus 2 equals to 4, that is the your perspective, you are saying in that particular way, but it can be 2 plus 2 in a hardware, it can be not the 4, it can be 4.00 or something, because now it depends, like, okay, which voltage, how you're going to convert that particular thing. But what I'm saying, if it is a commercial, can you do all these things? No. And then for this small experiment, you have to go through the everything is a complex one. So if it is something which you can design, if it is something which is a freeware, if it is something which is a open source, you can do small testing also. So that is very important. And the RISC-V, the why the RISC-V is nowadays is so boom, because at least in a hardware side, there is a one community, and they are giving us the flexibility of doing all these things. Now, when it comes to the workshop area, let's try to see, like, okay, uh, what are the different areas. So let me just start from here. So yeah, animation, just it's supposed to come later on. So the first one is a RISC-V architecture. Now I'm just trying to start from a RISC-V architecture. So I just gave an idea, like, okay, what does the RISC-V architecture inside the RISC-V architecture? Again, this is a whole the area where maybe we can have couple of such type of workshops. But I just gave an idea, like, okay, what is architecture I'm talking about, what is the importance of that. Now let's see, you have a RISC-V architecture. Now in the RISC-V architecture, what are the different things you can do as a research area? You can say, like, okay, using that architecture, they have a flexibility of a new ISA. I'm going to write a new ISA, and I'm going to design a new processor. So when I'm saying the new processor, basically, you can say, like, okay, I just want to do only 5 operations of a processor. Maybe tomorrow you will come and you will say, like, okay, I want to do the 50 operations of a processor. Now, when I'm saying 50 operations and the 5 operations, then you will say, like, okay, how come? Means the processor is a processor, and it should do everything. So, but what I'm saying, let us suppose as a researcher, you are saying using a 5 operations, you can do everything: addition, subtraction, shift right, and maybe the fifth one you can just choose maybe one more thing, maybe the increment. So you're saying with these 5 operations, I can design the whole processor. That means whatever be the code of a multiplication or the division, if someone has written in a some Java based program, and the back end of that, only the 5 operations are going to be happen. So that means you have only these 5 operations. That means your hardware can do only these 5 operations. Now, hardware can do only, you are going to design your hardware only for these 5 operations. That means if someone has to do the multiplication, then you have to design your circuit in such a way with these 5 operations, everything is going to be happen. So that's what I was talking about, the 5 operations. So maybe you want to do some research, like, okay, 5 operations, I want to do everything. Tomorrow, maybe you can say, like, okay, I can do all the operations, all the mathematical operations with those two functionality, like maybe addition, not even the addition with the, let us suppose you're saying with the shift right, shift left, I can do everything. So that's the research area I'm talking about. Like, okay, you are going to do, you're going to design a new processor, and this is basically you design it. If you want to do the IP, you can just do that particular part also. And this flexibility you will get from the RISC-V architecture point of view. And there are a lot of people they are doing on this particular area. Second thing is, now let us suppose you want to design a application. When I'm saying the application, you want to come up with a product. You're saying like, okay, there is a product in the market, and that is maybe some car controller, maybe some automatic car controller, something you want to design that particular thing. Now for that, now we are not talking about right now that you're going to design from the scratch. It's like you want to come up, you want to design a car controller, some device. So that become your application. Now in that particular application, now you have two options. The first option is you just use a commercial processor, because obviously in there you have to do certain processing, and for that you just use a commercial processor. Maybe you can take based on any architecture which is available in the market. You just go there, you just check them, like, okay, I need your processor, controller, whatever with the things are there. You just use the commercial tool to the RTL2GDS, like obviously then the backend portion, and you just fabricate it. So this is the one way which most of the big companies they're just following this particular part. The second way is you will say like, okay, I'm a research scholar, I'm in a college, I'm a uh, postgraduate student, I'm a PhD one. I don't have this much of money. I don't want to do that particular part, because then what is the different, and what about if this fabrication is not going to give me that particular result? So I need a low cost solution, and I just really want to do something there. So you will say like, okay, let me use a processor designed by some open source community. I think you are able to you will be able to understand what I'm talking about. The pre-designed processor. So someone has designed the processor. So here I was just talking about the processor. So there is a two team in your university. The one team, they developed this processor. So maybe you are going to use that particular processor. So this new processor you are using here, or maybe someone else, because in a Google, if you will go and if you just search, there are a lot of communities, and they are just going to provide you some processor, predefined processor, and that is free of cost. So like Aditya mentioned, you can easily download from the GitHub, and we will talk about that particular part. So you are going to use that particular processor, and then you're going to use the open source tool. Obviously, if you will go from here to the commercial tool, then again, that's not going to solve your problem. Then you have to see whether these are compatible or not. Now, compatibility is very important. Then you will say like, okay, yes, open source tool, I want to use the open source tool, and then I'm just going to do the RTL2GDS, the whole flow, and then I will just fabricate it. The best part in this particular approach, like, okay, if you want to do the iteration, you can do any point of a time. It's a low cost. You can do the research. You can do everything. Maybe you can do everything in terms of you can design your own processor also, and then you can just do use the open source tool RTL, GDS, and fabrication. Now, as a workshop, and if I will say the 10 days workshop with a 4-hour each, so 40 hours. Now, if you are thinking like, okay, as a even if we are expert, first of all, we are not expert end to end in each and everything, but still, if you are thinking we are expert, then it's very difficult for us to give you the idea of everything. So we had a choice, like, okay, we just focus on this particular part, but in the, I think last year we did it one form of this portion. One, when I'm saying the one form, that is just a one form of that. So even this particular area itself is a big area. Like even if we want to give in overview, maybe we can do everything in a single workshop, but if you want you to do end to end yourself, then overview is not the thing. We have to just explain you each and everything, and that's the reason this time in this particular workshop, the hands-on is very important, interaction is very important, because we want you to do yourself. So someone just asked, can I use my own Verilog code? Yes, you can use it. You can, or maybe what you can do right now is just follow uh, the the code which we are talking about, because then if you're going to interact with us, at least we can tell you like, okay, these are the things. Because if 300 400 people, everyone is going to use their own code, it's very difficult if you stuck somewhere. What I'm going to recommend you, just use the code which we can give it to you. Just explore that particular part, whatever the questions are there, just do that particular thing, and later on you can just try your own code. So that's the thing. Now within the whole, like I was just talking about, like, okay, there is a big area. We decided like, okay, let's focus on this particular part, the below one. We are going to do using a predefined, I would say, the RISC-V architecture based some module. We will ask you just to download it and use that particular part and just flush it. Just go through the open source tools, understand each and everything, how you can do the iteration there. If you have to plug in, plug out anything, how you can do that particular part, and then just make it as a fabrication. And maybe in some other the next FDP, or maybe the version 2, I would say, or just series 2, whatever the name you want to give it. So just consider this as a the first version of this particular series. And in the second one, maybe we will just go in the front end side, like, okay, how you're going to write the processor, and then the verification, all those things come into the picture. So that's basically the workshop area, at least in this workshop. Now I'm just losing the time. I think it is 1, and Firuza ma'am, if you can just tell me like, okay, how much time I have, I will just next 2 slides I will just cover accordingly, because that will take another 15 minutes.
Puneet, I think we are fine. So I think Firoza ma'am has restructured today's keynote to tomorrow. So you can take 15 minutes, and then I'll take 15 minutes for the tool installation, and we are good.
Great. That's great. So so everyone, just give you an idea about the okay. So I was just talking about like, okay, let me just give you an idea about this RTL2GDS flow a little bit. And uh, I'm sure like, okay, I cannot explain you everything in the next 15 minutes, but I will just give an overview, and just to remind you, basically, uh, refresh your memories. Okay, that's my goal for the next in the next 2 slides. So what is the front end to back end flow? So I was talking about system specification. It's just like whatever be the specification you want to design your circuit, then design the architectural design which we are talking about. So this is the architectural design where you have to design your the circuit, basically what your system as per the instruction set, as per the processor. Like I was talking about the 5 and the 50, it is that particular area where on the basis of your architecture of the hardware which you're going to use it, I would say, on the basis of that you are going to design the things like, okay, with the 5 different operations, you have to design the complete circuit, or with the 50 operations you have to design your circuit. That's somewhere this architectural design things come into the picture. Then after that, once this is designed, it is very easy. Like, okay, you can just do the functional design, the logic design, where we're talking about the code, the Verilog code which you're going to write it, and then you're going to do the circuit design, you're going to do the physical design. So when I'm talking about the circuit design, it is like in our colleges, we are doing this spice simulation and all those things. Some circuit we are drawing on a paper pen, but yes, with the tool we are going to do that particular thing. Then in a physical design, it is basically the how after the fabrication the things come into the picture. Now here in the physical design, we usually talk about in terms of on a CMOS, this transistor level, like a fabrication point of view, where a transistor is supposed to be placed. So in a circuit design, it's not about where exactly in a chip a particular transistor is going to be placed. That's the reason it's a circuit design. You just design a circuit and done. In a physical design, what you have to do in a chip, if it is this much of small chip or this much of small chip, where exactly a transistor T1 is going to place. It is going to place in the center, in the corner, in the bottom corner, and the right, left, whatever the thing. That is the physically we are going to design that particular part. Then obviously the verification is always important, whether it is meeting your specific your requirement or not. So that's a physical verification point of view. Then the fabrication, and then obviously the packaging testing, and then you will do the chip. You will get a chip. Now the question which is very important right now, and the difference between a academia portion or the research versus the industry. So people say like, okay, it's very easy, it's very easy flow. Yes, I can do that particular part. But frankly, guys, let me tell you from the industry perspective, this verification, this portion, if I will say, this is very time consuming, because if anything goes wrong here, it is going to be like the everywhere it is going to be like that only. Circuit design, we make sure like, okay, this is going to be 100% correct. Physical design, it's supposed to be 100% correct. And then we do the physical verification also. Like, okay, just do the physical verification and just make sure everything is correct. And then we talk about the fabrication. Now, if you are thinking like, okay, once this is done, it is very easy for the fabrication, or the fabrication companies, the foundries, they are also doing their own checks. Now, as a industry, we are talking in terms of billions, millions, dollars, and so we don't want to lose that particular part, and that's the reason there is a big team. Uh, Maybe hundreds, thousands of engineers are working on a single chip. So if Intel tomorrow is come up with the one processor, so if you are thinking like, okay, the 2 or 3 engineers can do everything, that's not possible. There is a huge team is there. But if you, as a research scholar and in a university environment, if you want to design a processor, like we were talking about your own processor, if you want to design your own processor, so do you think you will get a team of thousands of people, thousands of engineers? No, that's not possible. And if you as a engineer, as a PhD, you want to do something and you want to fabricate a chip. So that's nowadays university, they are saying like, okay, you should have your own chip fabricated by you. So do you think you can replace the work of thousands of engineers? No, that's not possible. And maybe you can say like, okay, my chip is very is less complex, so I will not take that much of time. But still, if you're thinking like, okay, you can do end to end yourself in a span of 1 year, it's very challenging for you. For that, you should know like, okay, uh, first of all, you have to reduce the complexity, and that complexity is not your design on your circuit. It is basically from the tool perspective, from the architectural point of view, you have to reduce that particular part. And that's what we are going to tell you, like, okay, even if a small chip, if you want to fabricate it, what exactly you have to do it. So we are talking, we are just so there are two approach. We usually talk in the VLSI, top to bottom and bottom to top. So here, if you say this is a top to bottom, like first go with the system specific architectural design and everything. So so basically, if you will see the big picture, it is just a architectural design. So we don't want to focus right now. It is in this particular thing. Like, okay, this is the thing. We are just trying to help you to fabricate a chip. And we are just thinking like, okay, for the time being, just use a open source or the RISC-V architecture as it is, and then just do rest of the thing. And if you are thinking like, okay, that is not a challenging, believe me, once you will go through the workshop, then you will come to know it's not that easy also. So we are just trying to close on that particular part. Just to give an idea, like, okay, what we do at this particular place. So it's not that easy. Again, there are RTL description, functional verification, logic synthesis, gate level netlist, logic verification and testing. So this is basically, we usually talk about the front end flow. Then we talk about the backend side and the backend physical. Then we're talking about the partitioning, chip planning, placement, clock tree synthesis, signal routing, timing closure. So Aditya already gave you a little bit idea about the day 2, 3, 4 till 10, what we are going to do. So you will see, we will talk about certain concept. We will talk about like, okay, in terms of the tool, open source tool. We will also talk about like, okay, a particular net list, a particular design, how you're going to do that particular part. And if those designs are based on the RISC-V architecture, then what are the different challenges you will face during that particular time. So if it is some commercial architectural based netlist, then it is very easy for you just to do everything. But if it is a RISC-V based, then maybe there may be some challenges. So we are going to discuss that particular part. One more thing which I just want to highlight here, maybe let us suppose you will say like, okay, what different you're going to do, how you're going to learn that particular part. So let us suppose if you have downloaded a particular netlist, which is a RISC-V architectural compatible, and if I will say like, okay, design, you just come up with your own design. So let us suppose in that particular place, it is some counter is written in some fashion. When I'm saying the counter is written in some fashion. So, okay, so take it this example. You have a uh, Verilog netlist. You have a netlist basically, which is some commercial compatible, commercial architecture, commercials ISA compatible. That particular thing is there. Now you want to convert that thing into a RISC-V. Then how you're going to do it? So for that, it's just like you have something counter related thing. You have to just understand like, okay, how you're going to write this particular counter in a RISC-V. Maybe you can just use a predefined code, or maybe the I would say from the GitHub or maybe the open source community. You can just check like, okay, how you're going to change this particular counter. So you can do those changes and you can just make your own RISC-V compatible design also, and then just try it where exactly you're going to fail, or where exactly there is some challenges, and just come up with the chip. So after this workshop, if all of you can come up with a one chip, so I think with anything, maybe a adder chip based on some RISC-V architecture base, I think that is more than enough for all of us. Our workshop, that everything is going to be the successful. Yeah, so I think let's like I said, I don't want to take a lot of time of you guys, and we will discuss about this thing in detail later on. Now, just from the Q&A point of view, if anyone have any question, maybe just let me know. I think. So Chandra Kumar, he was talking about front end, back end, important part. What I haven't added in this course. I think that is how to learn. Okay, so I think these are the different questions. I think we should workshop sessions. Okay, so GitHub repository. So from where should take?
I think we can start from maybe say Wasim is asking if processes are already either commercial or pre-designed.
Okay.
Why do we need to further do the processing? maybe I can answer that.
Yes,
So
please.
Wasim, not all processors are capable of doing everything. There are different processors. Even if you look at RISC-V environment, say you take processors from pulp environment in the ETX Zurich. So they have a family of processors which do different capabilities with respect to power, the kind of MAC units which are in there. Now, suppose you do not find one which completely suits your need. Maybe you need a floating point adder or a floating point MAC, which is not available. Maybe you find something with lesser memory. Maybe you find the need to further upgrade the MAC unit in terms of a precise addition in there, or maybe you find that you need to put a system bus in there to put an accelerator with it. So with respect to your particular application, what is available might not meet the power area trade-offs which you have. So that's why you need to know how to modify and test things on your own end. Then there is a question by Deepak, who is asking, how do we change a 32-bit processor to 64? That is a little more involved. Basically, everything from ISA to adders to everything changes. How far? So Shreyas has a good question. How efficient are, with respect to license versions? Open source tools are not at all efficient, to put it very simply. They are an investigation tool rather than optimization tool. What they let you do is investigate what your design is going to look like. Maybe if your specs are not very hard, make a version of your design. They also let you try some fancy things. Like, for example, I explained, maybe you want to put a very complex adder in which if you have Synopsys tools, maybe that Synopsys tool will automatically create that fancy adder. But here you can make that fancy adder yourself and substitute in the MAC unit, and then you can rerun using the open source tool, and you get the same or probably better performance than the Synopsys tool would have given. It lets you use your own ingenuity to make better things. Sure. I'll wait. You can do more than that, Naveen, not just that. So yeah, I think those are the general questions. I don't.
Yeah, so they're just talking about, can we design our own IP? Okay, so after this workshop, so IP, I think that topic is itself is a big one. So IP in the sense you should have a new functionality at least. So if you have an idea, you can fabricate it. You can just go with the till the hard IP. You can just you can talk about. So it's not about the soft IP. Maybe if you have some idea, you can convert into the hard IP. There's one more question. Someone is asking about the CMOS required to understand the physical design part of this course. So you should have a basic understanding. So it's not like depth knowledge. When I'm saying the depth, so again, this is something which is very subjective. So when I'm saying the subjective, maybe something which is basic for me is in depth for you. So I don't know, like what is what is the thing, but yes, as such, you should know the current. You should know how the CMOS usually work, the basic something about the layout diesel. I think that is more than enough if you talk about uh, this workshop. Then, well, we are just putting our netlist file and defines as of a core and the core, I think, yes. So
Maybe Naveen needs to understand that if it was so simple, then everyone would have made chips.
yes. So yes, I think the answer of your question is it is very simple and everyone can make the chip out of this, and that's our goal. That's the goal of this particular workshop. Like, we want to make it simple. So right now it's not that simple because there are certain areas where everyone is facing a lot of challenges. Like Aditya said, it's not very straightforward. Um, if you know, then it is very simple. If you don't know, it is, yes. So people will struggle with a lot of things. So it's going to be very good workshop, and I'm sure like Naveen, you can come up with something out of this workshop very easily. Then can I totally the news section extend the processor? I think yes. Answer is yes, but not in this workshop. Which foundries are allowing fabrication of an open source design? So as if you're talking about the foundries fabrication open source design, now we are not okay. So again, now there are two things. It's not about the open source design, it's about the technology which you are using for the fabrication. So they have foundries, there are you should have a PDK for that particular thing. So now right now you can say the foundry is a business. So foundry is like is a paid one, is a free one. So I think there is no open source foundry. It is basically maybe the free, not even the free foundry. It is basically institutional foundry. So if your institution has a tie-up with a particular foundry, so in India we have a couple of foundries within the institutions. So there you can do it. So if I understood your question, the fabrication, open source tools or the environment, just these are the two different things. The important thing is the technology node. So your question is supposed to be like, okay, these open source tools, are they compatible with this particular technology node? Now, yes, if that is the question, then definitely that we have to see it how complex verification they can do it. So that is not that's just something we're going to discuss a little bit. That it's not like okay, open source tool can handle each and everything, but yes, up to a certain limit they can do it. And if they are not able to do it, then another area where I will tell you like, okay, just go, it is an open source tool, just make changes in the tools and just make it compatible with the technology node. So you can do in that particular way also. Okay, so I think
yeah, maybe I can take a couple of questions and then I
yes.
can start the.
Yes.
There is an interesting question here which I wanted to take. Someone is asking why academics are still concerned with 180 nanometer tech when industry has reached 7 and 5 nanometer.
Okay.
So 7 and 5 nanometer run costs are, I think, millions and millions per mask also sometimes. So that's why academics are still concerned with 180. And the fact is, with respect to architecture evolution, people are now actually coming back to bigger technology nodes like 45 nanometer, 90 nanometer, because most of the applications we have in the real world can be easily solved even in 180 nanometer. Just because someone wants to make FPGAs at 5 nanometer doesn't mean you have to make all your designs at 5 nanometer. Your simple IoT applications all work at 180 nanometer. You don't need to make them 5 gigahertz applications. Making a 10 megahertz application is fine. So that's why academics are still interested in 180 nanometer, because that's where most value for money is. And that's where, especially in India, we can get the most out of it. So we'll use Sky 130 here. Apart from that, yeah, I think let's start with the installation part maybe, and we can. Ma'am, can I have the sharing rights?
Yes, sir, sure. We will be sharing with you sir. Yeah, so you can check the presenter right is already been given to you, sir. And thank you, Puneet, sir, for the talk. So participant, there is small change in the schedule. The expert lecture by the keynote speaker 2 will be scheduled on Tuesday, day 2 of this faculty development program. So now we will be having the next session to be delivered by Mr. Aditya Dalapoti, sir. So we would like to invite Aditya, sir. And thank you, Puneet, sir, for the session, sir.
Okay, thank you, ma'am. So as I mentioned, I'll come back at to the end of this session to give you an overview of what kind of installations we'll use in the course. We'll keep it a short session. The general idea is I want to give you overview. Obviously, most of you would not have Ubuntu or Linux environment with you. So it will take you time to get everything set up on your end. We'll put the notes and the installation guide in the provide that all to you so that you can do it on your own time. I wanted to overview what is the expectation. Some of these we'll also do along as we go along the course. So in general, the course is expected to have three major requirements. One is the CPP sim to give you some aspects of simulation and characterization. Then a lot of PNR and synthesis will be done using the OpenLane environment, which installs a bunch of tools from Yosys to Magic to OpenRoad to and a lot of other things. Also K-layout. But apart from that, we will also be investigating with respect to some tools in particular. So we expect some installations like Yosys, Python 3, FuseSock, Verilator, K-layout to be installed in isolation apart from the OpenLane installation itself. So these installations are actually quite easy. You can just do sudo apt-get for these. So I've just mentioned the list towards here at the end. If they are not present in your Ubuntu environment, you are going to need them. So now for the CPP sim, what I've done is I've put like an extensive guide here. You can, so this installation happens actually in Windows. You can go through this. I think there is a Mac version also available for Mac people. You can go through this guide in your own time and just do this installation. There are a couple of things which you have to be aware of to install this. In the next session, feel free to ask any questions if you have issues. So you should be able, following this guide, we have given this a few times before as well. People are able to quite easily install. With respect to the Linux environment, what I wanted to show is I want people to have the capability to at least install this on their own before we proceed with the workshop. Even if you have not been able to do it completely, it's fine, but you try this before you come to the next session. This and CPP sim, it would be useful because this, the use for this installation actually starts in like the 4th day of the workshop or something like that. So in the second day, it will be only CPP sim. Try to have CPP sim installed before the second day. If you have doubts with respect to this particular installation, even in the second day, that's fine. We can solve them towards the end of the first session on second day. This is what we want to achieve. I wanted to show you the rough structure on how you should target installing it. So say make any directory. So this is your Ubuntu environment. In this Ubuntu environment, I have already installed Git, Docker, and all those things using sudo apt-get. Once I have them, then these commands will run. So I would ask you to make a directory. For example, I'll run everything on E&ICT, FDP, RTL2GDS, make a similar directory on your own. Then just if you have Git on your end, you can just go here and then do this. Okay, sorry, test. And what you're supposed to do is you're supposed to clone this directory. Please try to clone the branch RC6 on the OpenLane Git. Don't clone other ones because we will follow most of the stuff on RC6, and it is easier to follow along with the rest of the team and understand what the script settings, configuration settings people have if they're all similar. So any questions up till this by the time this is running? Let's see, Q&A. Yeah, we'll give the PPT for sure. So I would advise at least have 4 GB partition on the RAM side and around 50-60 GB partition or even 30-40 GB on the memory side is fine. OpenLane is on Linux. You need to have virtual blocks on Linux. Yes, Naveen, if you already have Ubuntu, you just directly run these commands. There is a Linux version potentially of CPP-SIM, but it's fun because usually people have Windows environment. So I've given the Windows installation direct guide here. If you are able to easily install the Linux, there is a Linux version here. They have a good manual for Linux as well. Please feel free to install it in Linux. We'll only have a 1-day session on CPP-SIM trying to give you idea about how characterization is done. So it's fine. You can install it in Linux potentially. You don't need to install CPP-SIM in Linux. You only, if Linux, you can have CPP-SIM in Windows or Linux, either one. OpenLane, only Linux. It's only possible only in Linux. Fedora is a Linux, so actually, yeah, sure. Just one point to note, the CPP-SIM is a little edgy when if not used with the correct environment. So if your Linux distribution is not exactly the same, it will not really work out well. So that's why we prefer one particular method. So, but if you're able to make it work, it's fine. And as I mentioned, there'll be only one session on CPP-SIM, so you can probably follow along with it. So now CD, where we are, we go into this slide over here. So once you are here, once you have done this, I would advise you to, if you have Docker installed, I would advise you to quickly test if you are able to run the Docker. So for example, if I'm able to run the Docker, I see a bash environment at my end. After that, please exit the Docker, then go to OpenLane. In an OpenLane, there should be a library which got pulled called Docker build. In this Docker build, please type make merge. And if this make merge fails, if it says permission denied, you'll need to set chmod of some files to 666, like some docker.sock. This error will not come right now for me, but it might come for you. So I've kept it as a note over here. Now, after that, what you do is you go back here, and then you're supposed to provide the path where you are going to put your PDK. So for me, I advise you to put the path where in the initial directory you created, the test one. It's just for consistency reasons to follow along in this workshop. So this is the path I would advise you to keep home, whatever, and whatever folder you made. So we'll go, and what we'll do is we'll do export PDK root. This is the location where all your PDKs would be installed. So /home/technoready test1. Yes, we will share all this. Don't worry. So as I have mentioned, we will share this, and you will have time, ample amount of time. Next session is on Tuesday. That is only CPP-SIM. This all would be only expected by 4th session or something like that, depending on how it goes. So now we do this. I wanted to give you an upfront introduction to this because a lot of people were requesting for it. Now we go back to OpenLane after exporting, then we do make PDK. Then it will take some time to do make PDK. After the make PDK is done, what you can do is make test. And after doing the make test, you should see this. If you see this, then your environment has been correctly set up after doing make PDK and make test in OpenLane. That's the general overview. We will share this slide deck. We will share, we will be doing it one by one. I'm repeating it again for the next session. Only CPP-SIM is needed. Please have it preferably on your Windows. And Also, this session will be there on YouTube, at least for the for during this. You can follow along and go back to it, look at this, and try to run this. If you're not able to run this, come back to me in the next session and we'll talk about it. But for next session, only CPP SIM is needed. Any other questions? As I mentioned, Naveen, let's towards the next session, I will have some time at the end. I'll spare to take note of any issues you might encounter during the installations. But because for next session, we only need CPP SIM. So try to get CPP SIM installation done. Its documentation is already extensively there online. And I've also made an extensive guide to installing CPP SIM, which this will be uploaded online already for you guys. YouTube link for this session is already provided by Feroza ma'am to you guys. Yes, Pradyum, that's what I expected. 4 GB partition with respect to RAM and some 30-40 GB with respect to memory should be fine. Yes, prerequisites, you'll need to sudo apt get some of these things. So, okay, I think we are fine. So 4 GB RAM. Okay, I think ma'am, these are questions have already been answered. Ma'am, I'll share this slide deck with you as a PDF, and we should be good to go. Feroza ma'am. Hello, Feroza ma'am. Are you there?
Hello. Hello. Is my voice audible?
Yes.
Yeah. So ma'am is, I guess, busy with something. So with this, we come to an end of day one of this program. So I thank Aditya sir and Puneet sir for their presentation today. So all the participants are requested to please follow the links which are being provided in the important announcement portion. Okay, the YouTube playlist link is already been provided. In the playlist, you will get YouTube links of everyday lecture over there.
Okay. Ma'am, so I'll send the slides to Feroza ma'am, and please upload these so that people are able to follow along on the installation front.
Yeah, absolutely. It will be uploaded in the drive link. The drive link is already shared with the participants. So we request all the participants to follow up the drive link. The slides will be uploaded shortly. So another one announcement is there from our end. The course tomorrow and day after tomorrow, it will be off. So our next session will be from Tuesday onwards. So all the participants are requested to be connected on Tuesday, that is 30 of March. The session will start sharply by 9:30 onwards. So all the participants are requested to be connected till then so that we can start the session sharply by 9:30. So that's it from our end. Thank you all.
Perfect, ma'am. And yes, so as Washim is asking, I've listed to which softwares go in where in the slide deck so you can follow along. And rest all of them are basically sudo apt-get. And Sharmila, there is a Ubuntu installation guide in the CPP SIM website. You can follow that along. Perfect. Thank you, ma'am. I'll send these slides.
Yeah, thank you, sir. Thank you. Thank you. So dear participants, in case if you have any more queries after the session, you can let us know in the WhatsApp group, or you can also coordinate with the coordinators so that they can forward us your queries. We will get your queries solved by the experts and get back to you. So thank you all. So we request all the participants to please, yeah, WhatsApp group link. Yeah, Naveen Kumar sir, the WhatsApp group link is already provided in the mail. Or Naveen sir, you can also get back to your coordinator through whom you are coordinating. They will provide you the link. No, the YouTube videos don't have any deadline. It will be available anytime whenever you connect in your system. Okay. You will get the YouTube videos in the playlist link. The playlist link of YouTube is already been provided. The playlist will contain all the videos of day 1 to day 10 of the program. So for the WhatsApp group, you can contact to your respective coordinators. No, there will be no quiz on 30th of March. First quiz will be on 5th of April. That is day 5 of the program. First quiz will be on day 5. It is already being shared in this schedule itself. So you can have a look on that. The schedule is being already provided in the Google Drive link. That's it. Yeah, the installation guide will be provided in the Google Drive, sir. So it will be shortly provided. So we request you to please follow up with the Drive link. Each and every details will be there. In case if you are not finding anything, let us know through the coordinator respectively. So with this, we come to an end. Thank you, sir. Thank you, Aditya, sir. Thank you, Puneet, sir, for today's session. So we will meet on day 2 of the program, that is 30th of March, sharply by 9:30. So we request all the participants to please get disconnected. The event will be closed in next 5 minutes. Thank you all. Thank you. Bye.
Thank you.
Thank you, Aditi. So I think so we can end the event.
Yeah, absolutely, ma'am. I will be ending the event in next 2 minutes.
Okay. Thank you, Aditi. Thank you all for joining us. So we will be having our day 2 session on Tuesday. Thank you and happy Holi to all of you.